Hello aspirants, welcome to Magic World of Physics. In this video, we're going to discuss about some questions from Thermodynamics and Statistics which is asked in various exams like GATE, Barc, Chess, TIFF. Hope this video will be helpful for your coming Barc exam 2026. Without any further delay, let's get started. The first question is, consider a classical gas in thermal equilibrium at the temperature T1 and T2 where T1 less than T2. Which of the following graphs correctly represent the qualitative behavior of the probability density function of the x component of the velocity? We know that P of Vx is equal to m by 2 pi kt the whole raised to 1 by 2 into e raised to minus m Vx square by 2 kt. Here the range of Vx is minus infinity less than Vx less than infinity. This is equation number 1. And here when Vx tends to infinity, then e raised to minus m Vx square by 2 kpt is approximately equal to 1 by e raised to infinity, that is approximately equal to 0. And when Vx tends to minus infinity, then e raised to minus m Vx square by 2 kpt is approximately equal to 1 by e raised to infinity, that is approximately equal to 0. And when Vx is equal to 0, then P of Vx is equal to m by 2 pi kt the whole raised to 1 by 2. And here it is given that the temperature is increased to T2. That is T2 is greater than T1. So at high temperature, the number of gas molecules with the larger velocity is increased in population. So that the graph looks like this. So the answer is option C. Here we can also say that this is a perfect probability distribution, that is the integral of minus infinity to infinity P of Vx dx is equal to m by 2 pi kt the whole raised to 1 by 2 into integral over minus infinity to infinity minus m Vx square by 2 kt dvx. This is equal to m by 2 pi kt the whole raised to 1 by 2 into 2 pi kt by m the whole raised to 1 by 2. This is equal to 1. So here the option C is the right answer. The next question is, for a temperature T1 greater than T2, the qualitative temperature dependence of the probability distribution f of v of the speed v of a molecule in 3 dimensions is correctly represented by the following figure. Here the total curve area remains same even if the temperature is changed. That means even if the temperature is increased in such a way that T1 greater than T2, the curve area remains the same. But for high temperature, the distribution function shifts to higher velocity. Here the curve becomes broader and the maximum intensity is lowered. That is, here the T1 shifted to the higher velocity and also maximum intensity for T1 is lowered and it is broadened. So the correct option is option A. The next question is, in low density oxygen gas at low temperature, only the transition and rotational modes of the molecules are excited. The specific heat per molecule of the gas is dash. So here the gas mentioned is oxygen, so it is a diatomic molecule. So here the rotational degrees of freedom is 2 and the vibration degrees of freedom is exist only if the temperature is high. That is, the temperature should be greater than 1000 degrees Celsius. Here it is mentioned that the temperature is low, so vibrational modes is not considered here. So here the translational mode is 3 and the rotational mode is 2. So the total degrees of freedom is 5. That is U is equal to FkBT by 2, that is equal to 5 kBT by 2. That is C is equal to, that is, a specific heat capacity is equal to dou U by dou T is equal to 5 by 2 kB. So this is the answer. Next question is, the specific heat per molecule of a gas of diatomic molecules at high temperature is dash. So here the translational degrees of freedom is 3, rotational degrees of freedom is 2, vibrational degrees of freedom is 2. So the total degrees of freedom is 7. So U is equal to 7 by 2 kBT. That is du by dt is equal to 7 by 2 kB. So this is equal to 3.5 kB. So here the specific heat is 3.5 kB. The next question is, a thermally insulated chamber of dimensions L2L is partitioned in the middle. One side of the chamber is filled with 10 moles of an ideal gas at pressure P and temperature T, while the other side is empty. At T is equal to 0, the partition is removed and the gas is allowed to expand freely. The time to reach the equilibrium varies as dash. So here the time to reach the equilibrium is T is equal to L by V. we know that V is proportional to square root over T by M. So T is proportional to L by square root over T into square root over M. That is T is proportional to LT raised to minus 1 by 2. That is T is proportional to n power 0 LT raised to minus 1 by 2. The next question is, the pressure P of a gas depends on the number density rho of particles and the temperature T, as P is equal to kBT rho minus B2 rho square plus B3 rho cube, where B2 and B3 are positive constants, where TC, rho C and PC denotes the critical temperature, critical number density, critical pressure, etc. The ratio rho C kBTC by PC is equal to dash. So here P is equal to kBT rho minus B2 rho square plus B3 rho cube. This is equation number 1. So dou P by dou rho is equal to kBT minus 2B2 rho plus 3B3 rho square is equal to 0. This is equation number 2. Then d square P by d rho square is equal to minus 2B2 plus 6B3 rho. This is equal to 0. That is 2B2 is equal to 6B3 rho. That is B2 is equal to 3B3 rho. This is equation number 3. So equation number 2 and equation number 3 gives kBT minus 6B3 rho square plus 3B3 rho square is equal to 0. So here we know that T is equal to TC. So kBTC is equal to 3B3 rho square. This is equation number 4. So equation number 1 implies PC is equal to 3B3 rho cube minus 3B3 rho cube plus B3 rho cube. So PC is equal to B3 rho cube. This is equation number 5. So equation number 4 and 5 implies rho KB TC by PC is equal to 3B3 rho cube by B3 rho cube. This is equal to 3. So the answer is 3. The next question is, the van der Waals equation of the state for a gas is given by P plus A by V square into V minus B is equal to RT, where P, V and T represent the pressure, volume and temperature respectively. Here A and B are the constant parameters. At a critical point where all the roots of the above cubic root are degenerate, then the volume is given by dash. So here it is asking about the critical volume. So this can be explained by the curve of P versus V. So here when the temperature is increased to T4, so let's say T4 curve is the critical isotherm and T4 is the critical temperature Tc. And here at the T4 curve, the slope dou P by dou V is equal to 0. So by van der Waals equation we know that P is equal to RT by V minus B minus A by V square. This is equation number 1. Then dou P by dou V at T is equal to Tc is equal to 0. So we can write minus RT by V minus B the whole square plus 2A by V cube is equal to 0. That is T is equal to 2A into V minus B the whole square by R V cube. This is equation number 2. Substituting the value of 2 in 1, we can write P is equal to R by V minus B into 2A into V minus B the whole square by R V cube minus A by V square. That is P is equal to 2A into V minus B by V cube minus A by V square. This is equation number 3. Differentiating this equation number 3 with respect to V, that is dou P by dou V is equal to 0. We know that dou P by dou V is equal to 2A by V cube plus 2A into V minus B into minus 3 by V raised to 4 plus 2A by V cube is equal to 0. And here at the point of inflection, we know V is equal to Vc, that is 4A by Vc cube is equal to 6A into Vc minus B by Vc raised to 4, that is Vc is equal to 3B. So here the answer is Vc is equal to 3B. In this way, we can also find the critical pressure and the critical temperature value. That is, to find the critical pressure value, we can substitute the value of 4 in 3. That is, Pc is equal to 2A into 3B minus B by 27B cube minus A by 9B square. That is equal to A by 27B square. That is Pc is equal to A by 27B square. This is equation number 5. Substituting the value of 4 and 5 in 1, we get P is equal to RT by V minus B minus a by v square. That is p plus a by v square is equal to t by v minus p. That is vc minus b into pc plus a by vc square is equal to tc. That is 3b minus b into a by 27b square plus a by 9b square is equal to tc. That is tc is equal to 8a by 27 rp. So in this way we can also find the critical pressure and critical temperature value. Next question is the van der Waals equation for 1 mole of a gas is P plus A by V square into V minus B is equal to RT. The corresponding equation of states for n moles of this gas at pressure P, volume V and temperature is dash. Here it is given that P plus A by V square into V minus B is equal to RT for n is equal to 1 mole. For n moles we know V is equal to V by n, that is P plus A n square by V square into V by n minus B is equal to RT. That is P plus A n square by V square into V minus NB by n is equal to RT. That is P plus A n square by V square into V minus NB is equal to nRT. So here in this option A and C is the same option, so both are the correct answer. A and C are the correct answer. So the next question is the volume and temperature of a spherical cavity filled with the black body radiation are V and 300 K respectively. If it expands adiabatically to a volume 2V, its temperature will be closest to dash. So for an adiabatic expansion, we know that Vt cube is equal to a constant, that is V1 T1 cube is equal to V2 T2 cube, that is T2 cube is equal to V1 T1 cube by V2 the whole raised to 1 by 3, that is V1 by V2 the whole raised to 1 by 3 into T1. And this is equal to 1 by 2 the whole raised to 1 by 3 into 300, and this is equal to 240 Kelvin. Next question is the ratio Cp by Cv of the specific heat at constant pressure and volume of a monoatomic ideal gas in 2 dimension is dash. So here as it is mentioned that it is 2 dimension, we can write translational degrees of freedom as 2, that is U is equal to Nf by 2 into Kt, that is N into 2 by 2 into Kt, that is equal to Nkbt, that is equal to Rt, that is Cv is equal to du by dt and this is equal to R, and Cp is equal to Cv plus R, that is equal to R plus R, this is equal to 2R, and the ratio of Cp by Cv is equal to 2R by R and this is equal to 2. So the answer is 2. The next question is the equation of state of an ideal gas is PV is equal to RT. At very low temperature, the volume expansion coefficient 1 by V into dou V by dou T at constant pressure is dash. We know that the volume expansion coefficient alpha P is equal to 1 by V into dou V by dou T at constant pressure. And we know PV is equal to RT, that is R by Vp is equal to 1 by T. That is dou V by dou T at constant pressure is equal to R by P. So we can write alpha P is equal to 1 by V into R by P and this is equal to 1 by T. So here when T tends to 0, then alpha P is equal to 1 by T. So we can say that the alpha P diverges as 1 by T. The next question is, a cavity contains black body radiation in equilibrium at temperature T. The specific heat per unit volume of the photon gas in the cavity is of the form Cv is equal to gamma T cube, where gamma is a constant. The cavity is expanded to twice its original volume and then allowed to equilibrate at the same temperature T. The new internal energy per unit volume is dash. So here it is given that Cv is equal to gamma T cube, that is du is equal to integral over Cv dt, that is equal to integral over gamma T cube dt, that is equal to gamma T raised to 4 by 4. So the option D is the correct answer. The next question is the internal energy E of a system is given by E is equal to Bs cube by Vn, where B is a constant and another symbol having their usual meaning. The temperature of the system is equal to dash. So here it is given that E is equal to Bs cube by Vn. Then we know that du is equal to Tds minus Pdv and T is equal to dou U by dou S at constant volume, that is equal to dou E by dou S at constant volume. So differentiating E with respect to S, we get 3b S square by Vn. So the temperature of the system is 3b S square by Vn. Next question is, let delta W be the work done in a quasi-static reversible thermodynamic process. Which of the following statement about delta W is correct? Here we know that du is equal to dq minus dw, and if it is an adiabatic process, dq is equal to 0. That is, du is equal to minus dw, and we know that as u is a perfect differential, w is also a perfect differential. By this equation, du is equal to minus dw. So that we can say that option B is the right answer, because option B says that delta w is a perfect differential if the process is adiabatic. So this is the answer. The next question is, a given quantity of gas is taken from the state A to C reversibly by two path A to C directly and A to B to C as shown in the figure. During the process A to C, the work done by the gas is 100 joule and the heat absorbed is 150 joule. If during the process A gives B gives C, the work done by the gas is 30 joule, then the heat absorbed is dash. So here A can reach C by two paths, that is by A to C directly and by A to B to C. Then by A to C, we know that in this path dW is equal to 100 joule and dQ is equal to 150 joule. So that du is equal to dQ minus dW, and this is equal to 150 minus 100, that is 50 joule. And if we take the path A to B to C, here dW is equal to 30 joule and dQ is to be find out. And even if we follow A to B to C or A to C, we know that the initial and final point is same. So the internal energy is same, that is du is equal to 50 joule in this path also, that is dq is equal to du plus dw, that is equal to 50 joule plus 30 joule, and this is equal to 80 joule. So the answer is 80 joule. The next question is, a vessel has two compartments of volume V1 and V2 containing an ideal gas at pressure P1 and P2 and temperature T1 and T2 respectively. If the wall separating the compartments is removed, the resulting equilibrium temperature will be dash. Here the vessel has two compartments. In the first compartment, the volume is V1, pressure is P1, temperature is T1 and the specific heat capacity is CV. And in another compartment, the volume is V2, pressure is P2, temperature is T2 and the specific heat capacity is CV. And in compartment 1, we can write the internal energy U1 is equal to N1 CV T1, and in compartment 2, the internal energy U2 is equal to N2 CV T2. So U total is equal to U1 plus U2, that is equal to N1 CV T1 plus N2 CV T2. This is equation number 1. And if the wall that separates the vessel into two compartments is removed, then the specific heat capacity is CV, temperature is T, and the number of moles is N1 plus N2. Then the internal energy is U final is equal to N1 plus N2 into CVT. This is equation number 2. Equating 1 and 2, we can write N1 CVT1 plus N2 CVT2 is equal to N1 plus N2 into CVT. That is T is equal to N1 T1 plus N2 T2 by N1 plus N2. That is PV is equal to nRT. That is N is equal to PV by RT. Substituting this value, we get T is equal to P1 V1 T1 by RT1 plus P2 V2 T2 by RT2 divided by P1 V1 by RT1 plus P2 V2 by RT2, and this is equal to P1 V1 plus P2 V2 divided by P1 V1 by T1 plus P2 V2 by T2. So this is the answer. Next question is, 10 grams of ice at 0 degrees Celsius is added to a beaker containing 30 grams of water at 25 degrees Celsius. What is the final temperature of a system when it comes to thermal equilibrium? The specific heat of a water is 1 calorie per gram per degree Celsius, and latent heat of melting of ice is 80 calorie per gram. So here we know that the mass of ice is equal to 10 gram and the temperature of ice is 0 degrees Celsius and latent heat is equal to 80 calorie per gram and C is equal to 1 calorie per gram per degree Celsius. The heat required to melt 10 gram of ice is equal to m ice into latent heat of fusion, that is equal to 10 into 80, that is equal to 800 calorie. That is 800 calorie is needed to melt the 10 gram of ice. But the heat available with the 30 gram of water is mc/dt. That is 30 into 1 calorie per degree, gram per degree Celsius into 25, and this is equal to 750 calories. So here the available heat is 750, but heat required is 800 calories. So this means that the ice doesn't melt completely, so that the final temperature of ice is 0 degree Celsius, because here the required heat is more than the available heat. So here the ice doesn't melt completely, so that the final temperature is 0 degree Celsius. The next question is, two different thermodynamic systems are described by the following equation of state 1 by T1 is equal to 3 R N1 by 2U1 and 1 by T2 is equal to 5 R N2 by 2U2, where T12, N12, U12 are temperature, mole numbers and the internal energies of two systems, and R is the gas constant. Let U total denote the total energy when these two systems are put in contact and attain thermal equilibrium. The ratio U1 by U total is dash. So here the first system has the internal energy U1, temperature T1 and the mole number is N1. And in the second system has the mole number N2, internal energy U2 and temperature T2. We know U1 is equal to 3 by 2 N1 T1 R and U2 is equal to 5 by 2 R N2 T2. Therefore, U total is equal to U1 plus U2, and this is equal to 3 by 2 R N1 T1 plus 5 by 2 R N2 T2. That is, U1 by U total is equal to 3 by 2 R N1 T1 by 3 by 2 R N1 T1 plus 5 by 2 R N2 T2. In equilibrium, the temperature of both systems is equal. That is, T1 and T2 is equal to T. That is, U1 by U total is equal to 3N1 by 3N1 plus 5N2. The next question is, the entropy S of a thermodynamic system as a function of energy E is given by the following graph. The temperature of the phases A, B, C denoted by TA, TB, TC respectively satisfies the following inequalities. We know 1 by T is equal to dou S by dou E. That is equation number 1. For the curve B, it is a flat curve. So, dou S by dou E is equal to 0, as they are parallel to x-axis. That is, TB tends to infinity. So, TB is greater than TA and TC. So, here the internal energy of UC is greater than UA. That is, the temperature of C is greater than temperature of A. So we can write the order of temperature like this. That is, TA less than TC less than TB. The next question is, the pressure P of a fluid is related to its number density rho by the equation of state P is equal to A rho plus B rho square, where A and B are constant if the initial volume of the fluid is V0 and the work done on the system when it is compressed so as to increase the number density from an initial value of rho 0 to rho 0 is dash. Here it is given that P is equal to A rho plus B rho square. This is equation number 1, and we know rho is equal to number density, that is N by V. The work done on the system, that is W is equal to minus integral over P dV, that is minus of integral over V1 to V2 A N by V dV plus integral over V1 to V2 B N square by V square into dV. That is, W is equal to minus of A N ln of V2 by V1 plus Bn square into minus 1 by V2 plus 1 by V1. This is equation number 3. And we know at B1 rho is equal to rho 0, that is rho 0 is equal to n by v1, that is v1 is equal to n by rho 0, and here v1 is equal to v0, that is n is equal to v0 rho 0, and at v2 rho is equal to 2 rho 0, that is 2 rho 0 is equal to n by v2, and we know v2 is equal to n by 2 rho 0. That is v2 by v1 is equal to n by 2 rho 0 into rho 0 by n, and this is equal to half. Substituting all this value in equation number 3, we can write w is equal to minus of an ln 1 by 2 plus b n square into rho 0 by n minus 2 rho 0 by n. Here we know minus ln half is minus of ln 1 minus ln 2. ln 1 is 0, that is minus ln half is ln 2, that is this is equal to an ln 2 plus bn rho 0, that is a ln 2 plus b rho 0 into n, that is a ln 2 plus b rho 0 into, we know n is equal to v0 rho 0, so a ln 2 plus b rho 0 into rho 0 v0. So this is the answer. So option D is the answer. The next question is, when a gas expands adiabatically from volume V1 to V2 by a quasi-static reversible process, it cools from temperature T1 to T2. If now the same process is carried out adiabatically and reversibly, and T2 dash is the temperature of the gas when it has equilibrated, then so here we need to find the relationship between T2 dash and T2. Here actually two processes taking place. One is the adiabatic quasi-static reversible process, and other is the adiabatic irreversible process. In the adiabatic quasi-static reversible process, the temperature is changing from T1 to T2, and in the adiabatic irreversible process, the temperature is changing from T1 to T2 dash. So in both these cases, we know dq is equal to 0 as both are adiabatic. So we know the equation du is equal to dq minus dw. That is, as dq is equal to 0, we can write dw is equal to minus du. That is, du is equal to minus dw. That means the internal energy is negative here. Internal energy negative means U final is less than U initial. That is, T final is less than T initial. That means the temperature initially is greater than temperature final. So we can say that here cooling is taking place. And it is mentioned that the volume expansion in both these cases is from V1 to V2. So we know that the work done, as the first one is a reversible process and the second one is irreversible, but there is no change in the volume term. So we know that in the irreversible process, due to the frictional force, to take in account with the frictional force, we know that the work done of irreversible is greater than work done of reversible. As the work done for irreversible is greater, we can say that internal energy of irreversible is greater than internal energy of reversible. And we know the equation du is equal to ncv dt. So as du irreversible is greater than du reversible, we can write dt irreversible is greater than dt reversible. That is, in the reversible process, the temperature is changing from T1 to T2, and in the irreversible process, the temperature is changing from T1 to T2 dash. So we can say dt irreversible is greater than dt reversible means T2 dash minus T1 dash is greater than T2 minus T1. This implies T2 dash is greater than T2. So we can say that the correct relation between T2 dash and T2 is T2 dash greater than T2. So the answer is option B. The next question is, when an ideal monoatomic gas is expanded adiabatically from an initial volume V0 to 3V0, its temperature changes from T0 to T, then the ratio T by T0 is dash. So here it is mentioned that V0 is changing to 3V0 and T0 is changing to T0. and it is given that it is an adiabatic expansion. So as it is an adiabatic expansion, we can write PV gamma equal to a constant, and we know as it is an ideal gas, we can write PV is equal to nRT, that is P is equal to nRT by V. So we can write PV gamma equal to a constant means nRT by V into V gamma equal to a constant, that is TV raised to gamma minus 1 equal to a constant. So at V naught T naught, we can write T naught V naught raised to gamma minus 1 equal to a constant, and we can also write at 3V0 T, we can write T into 3V0 raised to gamma minus 1 equal to a constant. By equating these two equations, we can write T0 V0 raised to gamma minus 1 is equal to T into 3V0 raised to gamma minus 1, that is T by T0 is equal to V0 by 3V0 the whole raised to gamma minus 1, and this is equal to 1 by 3 the whole raised to gamma minus 1. And here it is given that it is a monoatomic gas. So for a monoatomic gas, the translational degrees of freedom is 3. So E is equal to 3 by 2 RT, that is EV is equal to du by dt, that is equal to 3 by 2 R, that is Cp is equal to Cv plus R, that is equal to 5 by 2 R, and gamma is equal to Cp by Cv, that is equal to 5 by 3. And it is here we given that here we find out that T by T naught is equal to 1 by 3 the whole raised to gamma minus 1, that is T by T naught is equal to 1 by 3 the whole raised to 5 by 3 minus 1, that is equal to 1 by 3 the whole raised to 2 by 3. So the answer is 1 by 3 the whole raised to 2 by 3, that is option B is the right answer. The next question is, a box separated by a movable wall has two compartments filled by monoatomic gas of Cp by Cv is equal to gamma. Initially the volume of two compartments are equal, but the pressure are 3 P0 and P0 respectively. When the wall is allowed to move, the final pressures in the two compartments become equal. So the final pressure is dash. So here we need to find the value of final pressure. Here a box is given and it is separated by a wall into two compartments, and one compartment is system A and another compartment is system B. So the system A has a pressure 3P0 and volume V0, and system B has a pressure P0 and volume V0. So initially the volume of system A and system B is equal. So when the wall is allowed to move, that means the volume of two systems changes so that the pressure of both the compartments become equal. Then what will be the final pressure? That is we need to find that. Okay. In the final condition, total volume V1 plus V2 is equal to 2V0. Let's take it as equation number 1. And in all the options given in the question, we can see a gamma. That means we should use the equation PV raised to gamma equal to a constant. That is, for system A, we can write 3P0 V0 raised to gamma is equal to PF V1 raised to gamma. That is, V1 is equal to 3P0 V0 raised to gamma by PF the whole raised to 1 by gamma. This is equation number 2. Then for system B, P0 V0 raised to gamma is equal to PF V2 raised to gamma. That is, V2 is equal to P0 V0 raised to gamma by PF the whole raised to 1 by gamma. This is equation number 3. Equation number 1, 2 and 3 implies V1 plus V2 is equal to 2V0, that is equal to 3P0 V0 raised to gamma by PF the whole raised to 1 by gamma plus P0 V0 raised to gamma by PF the whole raised to 1 by gamma. That is, 2V0 is equal to 3P0 by PF the whole raised to 1 by gamma into V0 plus P0 by PF the whole raised to 1 by gamma into V0. That is, PF raised to 1 by gamma is equal to 1 by 2 into 3P0 raised to 1 by gamma plus P0 raised to 1 by gamma. That is, PF raised to 1 by gamma is equal to P0 raised to 1 by gamma into 3 raised to 1 by gamma plus 1 by 2. That is, PF is equal to P0 by 2 raised to gamma into 1 plus 3 raised to 1 by gamma the whole raised to gamma. So the answer is option C. The next question is, a monoatomic gas of volume V is in equilibrium in a uniform vertical cylinder, the lower end of which is closed by a rigid wall and other by a frictionless piston. The piston is pressed lightly and released. Assume that the gas is a pure conductor of heat and the cylinder and the piston are perfectly insulating. If the cross-sectional area of the cylinder is A, the angular frequency of small oscillations of the piston about the point of equilibrium is dash. So here the gas is a poor conductor and it is perfectly insulating. That means it is an adiabatic process. That means dq is equal to 0. So we know that PV raised to gamma equal to a constant, and for a monoatomic gas gamma is equal to 5 by 3. So as PV raised to gamma equal to a constant, we can write derivative of PV raised to gamma equal to 0. That is dP V raised to gamma plus gamma PV raised to gamma minus 1 dV is equal to 0. That is dP is equal to minus gamma P by V dV. That is equal to minus gamma P by V. We know dV is equal to AdX. That is this is equal to minus gamma P by V into AdX. So in the equilibrium, the force exerted by the gas and the force exerted on the gas, that is on the piston, will be equal. That is mg is equal to Pa. And if the position of a piston is to be changed, that means an additional force is to be applied. That is dF is equal to AdP. And dF is equal to A into dP means minus gamma P by V into AdX. That is equal to minus gamma mga by V into dx. That is F is equal to integral over 0 to x into minus gamma A mg by V into dx. That is equal to minus gamma A mgx by V. That is equal to minus kx. And we know that k is equal to m omega square. That is k is equal to m omega square. That is equal to mg gamma A by V. From here we can write omega is equal to square root over gamma g A by V. And we know for an monoatomic gas, gamma is equal to 5 by 3. That is square root over 5 by 3 into Ga by V. Next question is, which of the following statements concern the coefficient of volume expansion alpha and the isothermal compressibility kappa of a solid is true? So here we need to find which statement is correct. So here alpha P is equal to 1 by V into dou V by dou T at constant pressure, and kappa T is equal to minus 1 by V into dou V by dou P at constant temperature. So here this is just like the specific heat Cp and Cv. So we can say alpha P and kappa T are inextensive variable. That means it is an intrinsic parameter. So the answer is option A. The next question is, a Carnot cycle operates as an heat engine between two bodies of equal heat capacity until their temperature become equal. If the initial temperature of the bodies are T1 and T2 respectively and T1 greater than T2, then their common final temperature is dash. So here it is given that the Carnot cycle is operating as a heat engine between two bodies. So let the body 1 is at the temperature T1 and having the specific heat capacity Cv, and the body 2 is at the temperature T2 and having the specific heat capacity Cv. So here from the body 1, Q1 heat is absorbed and the work is done, which is equal to W is Q1 minus Q2, and Q2 heat is rejected to body 2. So here the total entropy change delta S is equal to delta S1. This is because of body 1, and delta S2, that is this is due to the body 2, and plus delta S cyclic, and this is for cyclic substance. So here the initial and final points of the system is same because it is a cyclic process. So we can say that the delta S cyclic is 0. That means delta S is equal to delta S1 plus delta S2. That is for body 1. That means the temperature is changing from T1 to T. And we know that the T1 is greater than T2. That is here T is less than T1 and T is greater than T2. So here for the body 1, the temperature is changing from T1 to T. So the delta S1 is equal to integral over T1 to T dQ1 by T. That is equal to Cv integral over T1 to T dt by T. That is equal to Cv ln of T by T1. And for body 2, delta S2 is equal to Cv ln of T by T2. For a reversible process, we know the entropy change is 0. That is delta S is equal to 0. That is delta S1 plus delta S2 is equal to 0. That is Cv into ln of T by T1 plus ln of T by T2 is equal to 0. That is Cv of ln of T into T by T1 T2 is equal to 0. That is ln of T square by T1 T2 is equal to 0. We know ln 1 is equal to 0. That is T square by T1 T2 is equal to 1. And this gives T is equal to square root over T1 T2. So the answer is square root over T1 T2. That is option C is the answer. The next question is the heat capacity of the interior of a refrigerator is 4.2 kilojoule per Kelvin. The minimum work that must be done to lower the internal temperature from 18 degrees Celsius to 70 degrees Celsius when the outside temperature is 27 degrees Celsius will be dash. So here the temperature is changing from 18 degrees Celsius to 70 degrees Celsius. That means converting it to Kelvin, we can write it is changing from 291 Kelvin to 290 Kelvin. Here the temperature change is 1. So here Cv is equal to 4.2 kilojoule per Kelvin, and we know for a refrigerator the efficiency eta is equal to 1 by T1 by T2 minus 1. That is equal to 1 by 300 by 290 minus 1. This is equal to 29. And we know Q1, it is the heat that extracted from the source. That is Q1 is equal to Cv dt is equal to 4.2 kilojoule. Because we know that Cv is equal to 4.2 kilojoule and dt is equal to 1. So we know eta, that is equal to Q2 by W. That means W is equal to Q2 by eta. This gives 4.2 by 29, and this is equal to 0.14 kilojoule. So the answer is 0.14 kilojoule. The next question is the internal energy of a system at a fixed volume is found to depend on the temperature T as E of T is equal to AT square plus BT raised to 4. Then the entropy as a function of temperature is dash. So here E is equal to AT square plus BT raised to 4. This is equation number 1. Then by the first law of thermodynamics, we can write du is equal to dq minus dw. And here for a fixed volume dv is equal to 0. That is pdv is equal to 0. That is dq is equal to du. That is du is equal to tds. That is tds is equal to 2at plus 4bt cube into dt. That is ds is equal to 2a plus 4bt square into dt. Then after integration we can write delta s is equal to s final minus s initial, that is equal to 2at plus 4bt cube by 3 plus c. That is s final is equal to 2at plus 4 by 3 bt cube plus c plus s initial. That is equal to 2at plus 4 by 3 bt cube plus c1. So we can say that this is the answer. That is option C is the answer. The next question is a mole of gas at initial temperature Ti comes to contact with the reservoir of temperature Tf, and the system is allowed to reach equilibrium at constant volume if the specific heat of the gas is Ev is equal to alpha T, where alpha is a constant. Then the total change in the entropy is dash. So here dq is equal to du plus tw, and it is given that it is at a constant volume, that is tw is equal to 0. That is dq is equal to du. dq is equal to cv dt. This is equation number 1. And we know delta S gas is equal to integral over Ti to Tf dq by t. That is equal to integral over Ti to Tf cv dt by t. And this is equal to integral over Ti to Tf alpha t dt by t, because in this question it is given that Cv is equal to alpha t. So after integrating this we get delta S gas is equal to alpha into Tf minus Ti. This is equation number 2. And we know delta Q reservoir is equal to integral over Ti to Tf Cv dt. This is equation number 3. That is equal to integral over Ti to Tf alpha t dt, and this is equal to alpha by 2 into Tf square minus Ti square. That is delta S reservoir is equal to delta Q reservoir by T final. For the reservoir, the temperature is not changing. That's why we don't integrate for delta S reservoir. So here delta S reservoir is equal to alpha by 2Tf into Tf square minus Ti square. That is delta S is equal to delta S gas plus delta S reservoir. That is equal to alpha into Tf minus Ti plus alpha by 2Tf into Tf square minus Ti square. So this is the answer. The next question is the heat capacity Cv at constant volume of a metal as a function of temperature is alpha T plus Bt cube, where alpha and beta are constants. The temperature dependence of the entropy at the constant volume is dash. Here it is given that Cv is equal to alpha T plus beta T cube, where alpha and beta are constant. Then by the second law of thermodynamics, delta S is equal to integral over I2 of ds, and this is equal to integral over I2 of dq by t. And we know for constant volume W is equal to PdV, and this is equal to 0. So du is equal to dq, and this is equal to Cv dt. So we can write this is equal to integral over I2 of Cv dt by t, and this is equation number 1. Then this is equal to integral over I2 of alpha t plus beta t cube by t into dt, and this is equal to integral over I2 of alpha plus beta t square into dt. And this is equal to alpha t plus beta t cube by 3. The limits is from Ti to Tf. And here delta S is equal to Sf minus Si, and this is equal to alpha into Tf minus Ti plus beta by 3 into Tf cube minus Ti cube. And here Sf is equal to alpha Tf plus beta Tf cube by 3 plus Si minus alpha Ti minus beta by 3 into Ti cube. So here Si minus alpha Ti minus beta by 3 into Ti cube is S0. So we can write Sf is equal to alpha Tf plus beta Tf cube by 3 plus S0. So here S of t is equal to alpha t plus beta t cube by 3 plus S0. So this is the answer. The next question is an ideal Carnot engine extracts 100 joule from a heat source and dumps 40 joule to a heat sink at 300 Kelvin. The temperature of the heat source is dash. So here the source is at the temperature T1 and heat Q1 is absorbed from it, and work W is done, and Q2 heat is rejected to the sink at T2 temperature, that is 300 Kelvin. So here Q1 is given as 100 joule and Q2 is equal to 40 joule. So W is equal to Q1 minus Q2, and this is equal to 60 joule. And we know for Carnot engine, Q1 by T1 is equal to Q2 by T2. So T1 is equal to Q2 by Q1 into T2, that is equal to 100 by 40 into 300, that is equal to 750 Kelvin. So this is the answer. The next question is, two ideal gases in a box are initially separated by a partition. Let N1, V1, N2, V2 be the number of particles and volume occupied by the two systems. When the partition is removed, the pressure of the mixture at the equilibrium temperature T is dash. So here two ideal gas is separated by a partition initially. So here one gas have the number of particles N1 and volume V1, and another ideal gas having the number of particles N2 and volume V2. So after removing the partition, an equilibrium will arrive, and this the final temperature of that system is T. So V is equal to V1 plus V2, and the total number of moles N is equal to N1 plus N2, and this is equal to N1 by Na plus N2 by Na, and this is equal to N1 plus N2 by Na. So we know that PV is equal to nRT, and P is equal to nRT by V, and this is equal to N1 plus N2 by Na into, we know R is equal to NaKB, so NaKB T divided by V1 plus V2, and this is equal to KBT into N1 plus N2 divided by V1 plus V2. So the answer is option B. The next question is, the free energy of the gas of n particles in a volume V and a temperature T is F is equal to n kBT into ln of A0 V kBT the whole raised to 5 by 2 by n, where A0 is a constant and Kb denotes the Boltzmann constant. The internal energy of the gas is dash. Here it is given that F is equal to n kT into ln of A0 V into kT the whole raised to 5 by 2 by n. This is equation number 1. And we know F is equal to U minus Ts, that is U is equal to F plus Ts. And we know S is equal to minus dou F by dou T at a constant volume, and substituting this value in equation number 2, we get U is equal to F minus T into dou F by dou T at constant volume. If we substitute A0 V k raised to 5 by 2 by n as C, we can write equation number 1 as F is equal to n kT into ln of Ct raised to 5 by 2. And here dou F by dou T is equal to n k ln Ct raised to 5 by 2 plus n kT by Ct raised to 5 by 2 into C into 5 by 2 T raised to 5 by 2 minus 1. So here T into dou F by dou T at constant volume is equal to n kT ln Ct raised to 5 by 2 plus 5 by 2 n kT into 1 by Ct raised to 5 by 2 into Ct raised to 5 by 2 minus 1 plus 1. So T into dou F by dou T at constant volume is equal to F plus 5 by 2 n kT. This is equation number 4. So here U is equal to F minus T into dou F by dou T, and this is equal to F minus 5 by 2 n kT, and this is equal to minus 5 by 2 n kT. So the answer is option B. But in the option B, the negative sign is not given, but the most appropriate answer is option B. The next question is, consider the melting transition of ice into water at constant pressure. Which of the following thermodynamic quantities does not exhibit a discontinuous change across the phase transition? So here it is asking about the term that gives the continuous change. That means here when the ice is converting to water at constant pressure, that means it is the first order phase transition. In the first order phase transition, Gibbs free energy is continuous, and the first and the higher order derivatives of G with respect to temperature is discontinuous. So the continuous term here is Gibbs free energy. So the answer is option C. The next question is, for a particular thermodynamic system, the entropy S is related to the internal energy U and the volume V by S is equal to C U raised to 3 by 4 V raised to 1 by 4, where C is a constant. The Gibbs potential G is equal to U minus T plus PV for the system is dash. So here it is given that S is equal to C U raised to 3 by 4 V raised to 1 by 4. So U raised to 3 by 4 is equal to S by C V raised to 1 by 4. That is U is equal to S raised to 4 by 3 by C raised to 4 by 3 into V raised to 1 by 3. So T is equal to dou U by dou S, that is equal to 1 by C raised to 4 by 3 into V raised to 1 by 3 into 4 by 3 into S raised to 1 by 3, and this is equal to 4 by 3 into 1 by C raised to 4 by 3 into V raised to 1 by 3 into S raised to 1 by 3, and this is equal to 4 by 3 into 1 by C raised to 4 by 3 into V raised to 1 by 3 into C U raised to 3 by 4 into V raised to 1 by 4 the whole raised to 1 by 3, and this is equal to 4 by 3 into C raised to 1 by 3 by C raised to 4 by 3 into U raised to 1 by 4 into V raised to 1 by 12 divided by V raised to 1 by 3, and this is equal to 4 by 3 into U raised to 1 by 4 into C raised to 1 by 3 by C raised to 4 by 3 into V raised to 1 by 4, and this is equal to 4 U raised to 1 by 4 by 3 C V raised to 1 by 4. And here P is equal to minus dou U by dou V, and this is equal to minus S raised to 4 by 3 by C raised to 4 by 3 into dou by dou V of 1 by V raised to 1 by 3, and this is equal to minus S raised to 4 by 3 by C raised to 4 by 3 into minus 1 by 3 into V raised to minus 1 by 3 minus 1, and this is equal to 1 by 3 into S by C V raised to 4 by 3, and this is equal to 1 by 3 into S raised to 4 by 3 by C raised to 4 by 3 into V raised to 4 by 3, and this is equal to 1 by 3 into S raised to 4 by 3 by C raised to 4 by 3 into V raised to 1 by 3 into 1 by V, and this is equal to 1 by 3 into U by V. So here G is equal to U minus Ts plus PV, that is U minus 4 by 3C into U raised to 1 by 4 by V raised to 1 by 4 into C U raised to 3 by 4 into V raised to 1 by 4 plus 1 by 3 into UV by V, that is equal to U minus 4 by 3 U plus U by 3 is equal to 0. The next question is, a thermodynamic function G is equal to U minus Ts plus PV is given in terms of internal energy U, temperature T, entropy S, pressure P, volume V, and number of particles N. Which of the following relations is true? We know that G is equal to U minus Ts plus Vv, then dG is equal to du minus Tds minus SdT plus Pdv plus Vdp. So we know du is equal to Tds minus Pdv plus mu dn, that is dG is equal to Tds minus Pdv minus Tds minus SdT plus Pdv plus Vdp plus mu dn. So dG is equal to minus SdT plus Vdp plus mu dn. This is equation number 1. So here S is equal to minus dou g by dou t, and V is equal to dou g by dou p, and mu is equal to dou g by dou n. So the answer is option A. Next question is the relation between the internal energy U, entropy S, temperature T, pressure P, volume V, chemical potential mu, and number of particles N of a thermodynamic system is du is equal to Tds minus Pdv plus mu dn. Then U is an exact differential, implies that here it is given that du is equal to Tds minus Pdv plus mu dn. This is equation number 1. And here S, V, N are natural variables. T, P, V are redundant variable. And we know U is a exact differential. So dou by dou S of dou U by dou V is equal to dou by dou V of dou U by dou S. This is equation number 2. So from equation number 1 we can write T is equal to dou U by dou S at constant volume and number of particles, and P is equal to minus dou U by dou V at constant S and N, and mu is equal to dou U by dou N at constant S and V. So we can write equation 2 as minus dou P by dou S at constant N and V is equal to dou T by dou V at constant S and N. So this is the answer. The next question is the number of microstates of a gas of n particles in a volume V and of internal energy U is given by omega is equal to V minus Nb the whole raised to n into A U by n the whole raised to 3n by 2. Its pressure P, volume and temperature is related by dash. So here omega is equal to V minus Nb the whole raised to n into Au by n the whole raised to 3n by 2. This is equation number 2, and we know S is equal to Kb ln omega. So this is equal to Nkb ln V minus Nb plus 3 by 2 Nkb ln Au by n. This is equation number 2. So here du is equal to Tds minus Pdv plus mu dn. This is equation number 3. That is P is equal to minus dou U by dou V at constant S and N, and T is equal to dou U by dou S at constant N and V. Mu is equal to dou U by dou N at constant S and V. So we can write 1 by T is equal to dou S by dou U at constant N and V. So P into 1 by T is equal to minus dou U by dou V at constant S and N, and into dou S by dou U at constant N and V. So by reciprocity theorem we know that dou x by dou y at constant z is equal to minus dou x by dou z at constant y into dou z by dou y at constant x. So we can write P by T is equal to dou s by dou v at constant n and v. That is P by T is equal to nkb by v minus nb. This is equal to P into v minus nb is equal to nkbt. So this is the answer. The next question is the dispersion relation of a gas of non-interacting bosons in d dimension E of k is equal to a k raised to s, where a and s are positive constants. The Bose-Einstein condensation will occur for all values of dash. For one dimension, the energy of the non-relativistic particles is E is equal to p square by 2m. That is here p square is equal to px square, and for 2d energy is p square by 2m, that is p square is equal to px square plus py square, and for 3d E is equal to p square by 2m, that is p square is equal to px square plus py square plus pz square. So for a non-relativistic particle, the Bose-Einstein condensation only occurs in 3d case. For 1d and 2d case, Bose-Einstein condensation doesn't occur. But for a relativistic particle or a massless photon, the Bose-Einstein condensation doesn't occur in 1D, but it occurs in 2D and 3D. So here it is asking about the non-interacting bosons. Non-interacting bosons means it is a non-relativistic particle. For a non-relativistic particle, the Bose-Einstein condensation occurs only for 3 dimension. And here it is given that E is equal to a k raised to s, and for 3 dimension, for a non-relativistic particle, E is equal to p square by 2m, and that is equal to h cut square k square by 2m. Comparing 1 and 2, we can write S is equal to 2 and D is equal to 3. So that we can say D is greater than S. That means the answer is option A, because for a non-interacting boson, that means for a non-relativistic particle, the Bose-Einstein condensation occurs only for 3D in such a way that D greater than S. That is, the dimension should be greater than S. So the answer is option A. The next question is, in a system comprising of approximately 10 power 23 distinguishable particles, each particle may occupy any of 20 distinct states. The maximum value of entropy per particle is nearest to dash. We know that S is equal to KB, L and omega, where omega is the thermodynamic probability because it is the number of accessible microstate to the system. So for first particle, 20 different possibilities are there, and for second particle also there is 20 different possibilities, and for third particle also there is 20 different possibilities. That means for n particles there is 20 different possibilities. That is, omega is equal to omega 1 into omega 2 into omega 3 etc. into omega n, and this is equal to 20 into etc. into 20. It will comes 20 times, that is 20 power n. So S is equal to KB, L and omega, and that is equal to K, L and 20 raised to n, that is n KB, L and 20, that is S by n is equal to KB, L and 20. This is equal to 2.99 KB, that is approximately equal to 3 KB. So the answer is 3 KB. The next question is, in a thermodynamic system in equilibrium, each molecule can exist in 3 possible states with probabilities 1 by 2, 1 by 3 and 1 by 6 respectively. The entropy per molecule is dash. Here S is equal to minus K summation over I into Pi, L and Pi, where P is the probability, and we know that P1 is equal to half, P2 is equal to 1 by 3 and P3 is equal to 1 by 6. So S is equal to minus K half into Ln half plus 1 by 3 into Ln 1 by 3 plus 1 by 6 into Ln 1 by 6, that is equal to minus K into half into Ln 1 minus Ln 2 plus 1 by 3 into Ln 1 minus Ln 3 plus 1 by 6 into Ln 1 minus Ln 6. So this is equal to K into half Ln 2 plus 1 by 3 into Ln 3 plus 1 by 6 into Ln 2 plus Ln 3. So that we can write this is equal to K into 1 by 2 plus 1 by 6 into Ln 2 plus 1 by 3 plus 1 by 6 into Ln 3. So this is equal to K into 2 by 3 Ln 2 plus 1 by 2 Ln 3. The next question is, the balls of 10 different colors labeled by A is equal to 1, 2, etc. up to 10 are to be distributed among different colored boxes. A ball can only go in a box of the same color and each box can contain at most one ball. Let NA and capital NA denote respectively the number of balls and boxes of color A, assuming that NA greater than NA greater than 1. Then the total entropy can be best approximated by dash. So here let n1 balls of color 1 to be distributed in the n1 boxes of color 1 and n2 balls of color 2 to be distributed in the n2 boxes of color 2, etc. up to n10 balls of color 10 to be distributed in the n10 boxes of color 10. So we can write omega total is equal to n1 factorial by n1 factorial into n1 minus n1 the whole factorial plus n2 factorial divided by n2 factorial into n2 minus n2 the whole factorial plus etc. plus n10 factorial divided by n10 factorial into n10 minus n10 the whole factorial. This is equal to summation over a into na factorial divided by na factorial into na minus na the whole factorial. We know that S is equal to KB ln omega, that is KB summation over a into ln over na factorial by na factorial into na minus na the whole factorial. That is S by KB is equal to summation over ln of na factorial by na factorial into na minus na the whole factorial. That is S by KB is equal to summation over ln na factorial minus ln na factorial minus ln of na minus na factorial. This is equal to summation over na ln na minus na ln na plus na minus na into ln of na minus na minus na. So we can write S by KB is equal to na ln na minus na ln na minus na minus na into ln na minus na. So this is the answer. The next question is the Hamiltonian of a classical nonlinear one-dimensional oscillator is H is equal to 1 by 2m p square plus lambda x raised to 4, where lambda greater than 0 is a constant. The specific heat of a collection of n independent such oscillator is dash. For a single oscillator, the partition function Z1 is equal to 1 by h integral over minus infinity to infinity integral over minus infinity to infinity e raised to minus beta h dx dpx. So here h is equal to 1 by 2m p square plus lambda x raised to 4. So this is equal to 1 by h into integral over minus infinity to infinity integral over minus infinity to infinity e raised to minus beta into px square by 2m plus lambda x raised to 4 into dx dpx. So this is equal to 1 by h into integral over minus infinity to infinity e raised to minus beta lambda x raised to 4 dx integral over minus infinity to infinity e raised to minus beta px square by 2m into dpx. Let the first integral be I1 and second integral be I2. So we can write this is equal to 1 by h into I1 into I2. This is equation number 1. We know that integral over minus infinity to infinity e raised to minus alpha x square dx is equal to square root over pi by alpha. So we can write integral over minus infinity to infinity e raised to minus beta px square by 2m into dpx is equal to 2 pi m by beta the whole raised to 1 by 2. That is minus infinity to infinity e raised to minus beta lambda x raised to 4 into dx is equal to 2 into integral over 0 to infinity e raised to minus beta lambda x raised to 4 into dx. This is equation number 3. Let beta lambda x raised to 4 be y. We can write x is equal to 4y by beta lambda the whole raised to 1 by 4. So we can write x raised to 3 is equal to 4y by beta lambda the whole raised to 3 by 4. So dy is equal to 4 beta lambda x cube dx. So dx is equal to dy divided by 4 beta lambda x raised to 3. Substituting the value of x cube here, we can write this is equal to dy divided by 4 beta lambda into y by beta lambda the whole raised to 3 by 4. So this is equal to y raised to minus 3 by 4 by 4 into beta lambda the whole raised to 1 by 4 into dy. Then equation 3 implies 2 integral over 0 to infinity e raised to minus beta lambda x raised to 4 dx is equal to 2 integral over 0 to infinity e raised to minus y raised to minus 3 by 4 by 4 beta lambda the whole raised to 1 by 4 into dy. So this is equal to half into integral over 0 to infinity e raised to minus y into y raised to minus 3 by 4 into 1 by beta lambda the whole raised to 1 by 4 into dy. So this is equal to half into 1 by beta lambda the whole raised to 1 by 4 into integral over 0 to infinity e raised to minus y into y raised to 1 by 4 minus 1 dy. So this is equal to 1 by 2 into 1 by beta lambda the whole raised to 1 by 4 into gamma of 1 by 4. So this is equation number 4. Equation number 1 implies Z1 is equal to 1 by h into I1 into I2 and this is equal to 1 by h into 1 by 2 into 1 by beta lambda the whole raised to 1 by 4 into gamma 1 by 4 into 2 pi m by beta the whole raised to 1 by 2. This is equation number 5. So taking the all the constant as c, we can write Z1 is equal to c beta raised to minus 3 by 4. We know E is equal to minus dou by dou beta of ln Z1, that is equal to minus dou by dou beta of ln c b raised to minus 3 by 4. So this is equal to minus 1 by c beta raised to minus 3 by 4 into c beta raised to minus 3 by 4 minus 1 into minus 3 by 4. So this is equal to 3 by 4 into beta raised to minus 1. This is equal to 3 by 4 beta. So this is equal to 3 by 4 kbt. So for n oscillation, u is equal to n into e. This is equal to 3n by 4 kbt. So we can say cv is equal to dou u by dou t. This is equal to 3 by 4 n kb. So this is the answer. The next question is the angular frequency of the oscillation of a quantum harmonic oscillator in 2 dimensions is omega. If it is in contact with an external heat bath at temperature T, its partition function is dash. The energy spectra of the harmonic oscillator is En is equal to n plus half into h cut omega, where n is equal to 0, 1, 2, etc. Here the partition function Z1 is equal to summation over n equal to 0 to infinity e raised to minus beta en, that is equal to summation over n equal to 0 to infinity e raised to minus beta n plus half into h cut omega. This is equation number 1. That is equal to e raised to minus beta h cut omega by 2 plus e raised to minus 3 by 2 beta h cut omega plus e raised to minus 5 by 2 beta h cut omega plus e raised to minus 7 by 2 beta h cut omega plus etc. So this is equal to e raised to minus beta h cut omega into 1 plus e raised to minus beta h cut omega plus e raised to minus 2 beta h cut omega plus e raised to minus 3 beta h cut omega plus etc. So this is a GP. So we can say the common ratio is R is equal to e raised to minus beta h squared omega. So the summation can be written as e raised to minus beta h squared omega into 1 by 1 minus e raised to minus beta h squared omega. So for a non-interacting and indistinguishable particles, that means for a two-dimension, the partition function can be written as z2 and this is equal to z1 the whole raised to 2. So this is equal to e raised to minus beta h squared omega by 2 divided by 1 minus e raised to minus beta h squared omega the whole square. This is equal to e raised to minus beta h squared omega by 1 minus e raised to minus beta h squared omega into e raised to beta h squared omega by e raised to beta h squared omega into e raised to minus beta h squared omega by 2 divided by 1 minus e raised to minus beta h squared omega into e raised to beta h squared omega by e raised to beta h squared omega. This is equal to e raised to beta h squared omega by 2 by e raised to beta h squared omega minus 1 into e raised to beta h squared omega by 2 divided by e raised to beta h squared omega minus 1. This is equal to e raised to beta h squared omega by e raised to beta h squared omega minus 1 the whole square. So this is the answer. The next question is the Hamiltonian of two particles each of mass m is h is equal to p1 square by 2m plus p2 square by 2m plus k into q1 square plus q2 square plus 1 by 4 q1 q2 where k greater than 0 is a constant. Then the value of partition function z is equal to integral over minus infinity to infinity dq1 integral over minus infinity to infinity dp1 integral over minus infinity to infinity dq2 integral over minus infinity to infinity dp2 e raised to minus beta h is dash. So here result of beta is equal to integral over minus infinity to infinity dq1 integral over minus infinity to infinity dq2 integral over minus infinity to infinity e raised to minus beta p1 square by 2m dp1 integral over minus infinity to infinity e raised to minus beta p2 square by 2m dp2 e raised to minus beta k q1 square plus q2 square plus 1 by 4 q1 q2. So here we know that integral over minus infinity to infinity e raised to minus alpha x square dx is equal to square root over pi by alpha. So the equation 1 can be written as is equal to minus infinity to infinity dq1 integral over minus infinity to infinity dq2 into 2 square root over m pi by 2 beta into 2 into square root over m pi by 2 beta into e raised to minus beta k q1 square plus q2 square plus 1 by 4 q1 q2. So this is equal to 4 m pi by 2 beta into integral over minus infinity to infinity dq1 integral over minus infinity to infinity dq2 e raised to minus beta k into q2 square plus 1 by 4 q1 q2 e raised to minus beta k q1 square. So this is equal to 2m pi by beta into integral over minus infinity to infinity dq1 integral over minus infinity to infinity e raised to minus beta k into q2 plus q1 by 8 the whole square minus q1 by 8 the whole square into dq2 into e raised to minus beta k q1 square. This is equation number 2. Let y is equal to beta k into q2 plus q1 by 8 the whole square. Equation number 3, that is dy is equal to 2 beta k into q2 plus q1 by 8 into dq2. That is dq2 is equal to dy by 2 beta k into q2 plus q1 by 8 and this is equal to dy by 2 into square root over beta k into root beta k into q2 plus q1 by 8. This is equal to dy by 2 into root beta k into y raised to 1 by 2. This is equation number 4. So substituting these values in equation number 2, we can write equation number 2 as z is equal to 2m pi by beta into integral over minus infinity to infinity dq1 into integral over minus infinity to infinity e raised to minus y into y raised to minus 1 by 2 into dy by 2 root beta k e raised to beta k q1 square by 64 minus beta k q1 square. This is equal to 2m pi by beta into 1 by 2 root beta k integral over minus infinity to infinity dq1 into integral over minus infinity to infinity e raised to minus y into y power 1 by 2 into dy e raised to minus 63 into beta k q1 square by 64. So this is equal to 2m pi by beta into 1 by 2 root beta k integral over minus infinity to infinity dq1 into 2 root pi into e raised to minus 63 by 64 into beta k q1 square. We know that integral over minus infinity to infinity e raised to minus alpha x square is equal to square root over pi by alpha. So this is equal to 2m pi root pi by beta root beta k into pi into 64 by 63 beta k. So this is equal to 2m pi square by k beta square into root of 64 by 63. So this is the answer. Next question is, a particle is confined to the region x greater than or equal to 0 by a potential which increases linearly as u of x is equal to u0 x. The mean position of the particle at the temperature T is dash. Your expectation value of x is equal to integral over x px dx divided by integral over 0 to infinity px dx. This is equal to integral over 0 to infinity into x e raised to minus beta e divided by integral over 0 to infinity into e raised to minus beta e. So this is equal to, we know E is equal to P square by 2m plus U0x. So this is equal to integral over 0 to infinity e raised to minus Px square by 2m kt integral over 0 to infinity x into e raised to minus U0x by kt dx divided by integral over 0 to infinity e raised to minus P square by 2m kt dp integral over 0 to infinity e raised to minus U0x by kt dx. This is equal to integral over 0 to infinity x0 e raised to minus U0x by kt dx divided by integral over 0 to infinity e raised to minus u0x by kt dx. Here we put u0x by kt is equal to t. So as x tends to 0, t tends to 0, and at x tends to infinity, t tends to infinity. So x is equal to kt t by u0 and dx is equal to kt by u0 dt. So the integral can be rewritten as kt by u0 the whole square integral over 0 to t e raised to minus t dt divided by kt by u0 into integral over 0 to infinity e raised to minus t dt. So this is equal to kt by u0. So the answer is kt by u0. The next question is, consider a system of n non-interacting spins, each of which has a classical magnetic moment of magnitude mu. The Hamiltonian of the system in an external magnetic field H is summation I equal to 1 to n mu I H, where mu I is the magnetic moment of ith spin. The magnetization per spin at the temperature T is dash. So here we need to find the magnetization per spin, that is equal to m by n. The partition function Zn is equal to Z1 the whole raised to n. So we know that Z1 is equal to summation over e raised to minus beta ei. Here the interaction energy of a dipole E is equal to minus mu h cos theta. So this is equal to summation over e raised to beta mu h cos theta I. This is equation number 2. And we know that mu z is equal to mu cos theta. The net magnetization along the z direction is mz, that is equal to n mu z, that is equal to n mu cos theta, that is n into summation of theta into mu cos theta into e raised to beta mu h cos theta divided by summation over theta I into exponential over beta mu h cos theta. So this is equal to n into mu cos theta into summation over theta I into exponential over beta mu h cos theta beta divided by summation over theta I into exponential over beta mu h cos theta into beta. So this is equal to n by beta into dou by dou h of ln z1. So this is equation number 2. To determine the value of z1, so here we know that theta I can take any random value, that is we will consider a 3D distribution, that is z1 is equal to integral over 0 to 2 pi integral over 0 to pi e raised to beta mu h cos theta sin theta d theta d phi. So this is equal to 2 pi integral over 0 to pi e raised to beta mu h cos theta sin theta d theta. So here x is equal to, we consider that let x be minus cos theta, that is dx is equal to sin theta d theta. So at theta is equal to 0, it will change to x is equal to minus 1, and at theta is equal to pi, x is equal to 1. So the integral changes like this. This is equal to 2 pi into integral over minus 1 to 1 e raised to minus beta mu h x dx. This is equal to 2 pi e raised to minus beta mu h x by minus beta mu h. The limits are starting from minus 1 to 1. This is equal to 2 pi by minus beta mu h into e raised to minus beta mu h minus e raised to beta mu h. So this is equal to 2 pi by beta mu h into e raised to beta mu h minus e raised to minus beta mu h. This is equal to 4 pi by beta mu h into sin h beta mu h. And we know m is equal to n by beta into dou by dou h of ln z1. So this is equal to n by beta into dou by dou h of ln of 4 pi by beta mu h into sin h of beta beta mu h. So this is equal to n by beta into 1 by 4 pi by beta mu h sin h beta mu h into dou by dou h of 4 pi by beta mu h sin h beta mu h. So this is equal to n by beta into beta mu h by 4 pi sin h beta mu h into 4 pi by beta mu into 1 by h cos h beta mu h into beta mu minus 1 by h square sin h beta mu h. So this is equal to n mu into cos h beta mu h by sin h beta mu h minus 1 by beta mu h. This is equal to n mu into cot h beta mu h minus 1 by beta mu h. And here we know that cot h beta mu h minus 1 by beta mu h is the Langevin function. So this is equal to minus 1 minus n mu Langevin function of beta mu h. So the answer is option B. The next question is, a gas of n non-interacting particle is in thermal equilibrium at temperature T. Each particle can be any of the possible non-degenerate states of energy 0, 2e and 4e. The average energy per particle of the gas when beta e less than 1 is dash. Here the energy levels are 0, 2e, 4e. The partition function is equal to summation over gi e raised to minus beta ei. So we know that gi is equal to 1 as it is non-degenerate. So it is equal to 1 plus e raised to minus 2 beta e plus e raised to minus 4 beta e. So e is equal to minus dou by dou beta of ln z. That is equal to minus dou by dou beta of ln of 1 plus e raised to minus 2 beta e plus e raised to minus 4 beta e. That is equal to minus 1 by 1 plus e raised to minus 2 beta e plus e raised to minus 4 beta e into minus 2 e raised to minus 2 beta e plus minus 4 e into e raised to minus 4 beta e. This is equal to 2e e raised to minus 2 beta e plus 4e e raised to minus 4 beta e divided by 1 plus e raised to minus 2 beta e plus e raised to minus 4 beta e. And here we know that beta e is less than 1. So by binomial expansion we can write e raised to minus beta e is approximately equal to 1 minus beta e. So this is equal to 2e into 1 minus 2 beta e plus 4e into 1 minus 4 beta e divided by 1 plus 1 minus 2 beta e plus 1 minus 4 beta e. So this is equal to 1 minus 2 beta e into 2e plus 4e minus 8 beta square e square by beta. As beta e is less than 1, beta square into e square is less than 1. So this term can be neglected. That is, the last term can be neglected. So this is equal to 6e by 3. That is equal to 2e. So the answer is option A. Next question is, a one-dimensional chain consists of a set of n rods each of length a. When stretched by a load, each rod can align either parallel or perpendicular to the length of the chain. The energy of a rod is minus E when perpendicular to it. When the chain is in thermal equilibrium at temperature T, its average length is dash. So here let n1 be the rods perpendicular to the chain and n2 be the rods parallel to the chain. So here we assume that the energy when it is aligned parallel is E and energy when it is aligned perpendicular is minus E. So we know that the expectation value of x is equal to summation over xi pi. So we can write the expectation value of L is equal to summation over Li pi. The probability of minus E is equal to e raised to minus beta into minus E by e raised to minus beta E plus e raised to beta E. This is equal to 1 by 1 plus e raised to minus 2 beta E. This is equation number 1. Then the probability when it is arranged in parallelly, so that the probability is P of E, that is equal to e raised to minus beta E divided by e raised to minus beta E plus e raised to beta E. This is equal to 1 by 1 plus e raised to 2 beta E. This is equation number 2. So we can write L is equal to n1a P of E plus n2a P of minus E. This is equal to n1a into 1 by 1 plus e raised to 2 beta E plus n2a into 1 by 1 plus e raised to minus 2 beta E. So this is equal to n1a into 1 plus e raised to 2 beta e plus n2a into 1 plus e raised to minus 2 beta e divided by 1 plus e raised to minus 2 beta e into 1 plus e raised to 2 beta e. From the equation of P of minus E and P of E, we understood that P of minus E is greater than P of E. So in the equation n is equal to n1 plus n2, we can write n1 is approximately equal to n because n2 is approximately equal to 0. So we can write L is equal to Na divided by 1 plus e raised to minus 2 beta e. So the answer is option C. The next question is, a gas molecules of mass m are confined in a cylinder of radius r and height L, kept vertically in the earth gravitational field. The average energy of the gas at low temperature such that mgl greater than kBt is given by dash. Here h is equal to p square by 2m plus mgz, that is equal to px square plus py square plus pz square by 2m plus mgz. This is equation number 1. The single particle partition function z1 is equal to 1 by h cube into integral of e raised to minus beta h d omega, and we know d omega is equal to dx dy dz dpx dpy dpz. So this is equal to 1 by h cube into integral over minus infinity to infinity e raised to minus px square by 2m kt dpx integral over minus infinity infinity e raised to minus py square by 2m kt dpy integral over minus infinity to infinity e raised to minus py square by 2m kt dpz double integral over dx dy integral over 0 to L e raised to minus mg z dz. And we know that double integral over dx dy, that is the base area of cylinder, that is equal to pi r square, and we know that 0 to L into e raised to minus mg z by kt is equal to e raised to minus beta mg z by minus beta mg. The limit starts from 0 to L. So this can be written as 1 minus e raised to minus beta mgl by beta mg. So z1 is equal to pi r square into 2m pi kt by h square the whole raised to 3 by 2 into 1 minus e raised to minus beta mgl by beta mg. So this is equal to pi r square into m by 2 pi h cut square beta the whole raised to 3 by 2 into 1 minus e raised to minus beta mgl by beta mg. This is equation number 2. So z1 is equal to pi r square by mg into m by 2 pi h cut square into beta raised to minus 5 by 2 into 1 minus e raised to minus beta mgl. So we can write the pi r square by mg into m by 2 pi h cut square the whole raised to 3 by 2 as c. So this can be rewritten as z1 is equal to c into beta raised to minus 5 by 2 into 1 minus e raised to minus beta mgl. So ln z1 is equal to ln c beta raised to minus 5 by 2 into 1 minus e raised to minus beta mgl. We know that E is equal to minus dou by dou beta of ln z1, that is equal to minus dou by dou beta of ln of c beta raised to minus 5 by 2 into 1 minus e raised to minus beta mgl, and this is equal to minus 1 by c beta raised to 5 by minus 5 by 2 into 1 minus e raised to minus beta mgl into c into minus 5 by 2 into beta raised to minus 5 by 2 minus 1 into 1 minus e raised to minus beta mgl plus beta raised to minus 5 by 2 into minus e raised to minus beta mgl into minus mgl, and this is equal to 5 by 2 into beta raised to minus 1 minus mgl e raised to minus beta mgl divided by 1 minus e raised to minus beta mgl, and this is equal to 5 by 2 kbt minus mgl divided by e raised to beta mgl minus 1. This is equation number 3. We know that mgl is greater than kt, that is mgl by kt is greater than 1. So e raised to beta mgl minus 1 is approximately equal to e raised to beta mgl. So this can be rewritten as 5 by 2 kbt minus mgl into e raised to minus beta mgl. This is equal to 5 by 2 kbt minus mgl into e raised to minus mgl by kt, and we know that mgl by kt is greater than 1. So e raised to mgl by kt is very large, that means 1 by e raised to mgl by kt is equal to e raised to minus mgl by kt tends to 0. So the second term disappears. So E is equal to 5 by 2 kbt, that is U is equal to n into E, that is equal to 5 by 2 n kbt. So this is the answer. The next question is, a system has two normal modes of vibration with frequency omega 1 and omega 2 is equal to 2 omega 1. What is the probability that at temperature T the system has an energy less than 4 h cut omega 1? We know that E n1 n2 is equal to n1 plus half into h cut omega 1 plus n2 plus half into h cut omega 2. n1 and n2 take the values from 0, 1, 2, 3, etc. And here it is asked about the energy that is less than 4 h cut omega, that is E n1 n2 should be less than 4 h cut omega. So here E00 is equal to 0 plus half into h cut omega 1 plus 0 plus half into h cut omega 2. Here omega 2 is equal to 2 omega 1, that is this is equal to 0 plus half into h cut omega 1 plus 0 plus half into h cut into 2 omega 1. This is equal to 3 by 2 into h cut omega 1. So similarly we can find E01 is equal to 7 by 2 h cut omega 1, E20 is equal to 7 by 2 h cut omega 1, E02 is equal to 11 by 2 h cut omega 1, E30 is equal to 9 by 2 h cut omega 1, E10 is equal to 5 by 2 h cut omega 1. So the probability of energy less than 4 h cut omega is equal to 1 by z into e raised to minus 3 by 2 beta h cut omega 1 plus e raised to minus 5 by 2 beta h cut omega 1 plus 2 e raised to minus 7 by 2 beta h cut omega 1, and this is equal to, we know that x is equal to e raised to minus beta h cut omega 1, so this is equal to 1 by z into x raised to 3 by 2 into 1 plus x plus 2x square. So the answer is option D. Next question is, a system of n classical non-interacting particles each of mass m is at temperature T and is confined by the external potential V of r is equal to 1 by 2 into a r square, where a is a constant in 3 dimension. The internal energy of the system is dash. Here V of r is equal to half a r square, and this is equal to half a x square plus y square plus z square, and we know h is equal to px square plus py square plus pz square by 2 plus a by 2 into x square plus y square plus z square. This is equation number 1. And the partition function for a single particle z1 is equal to 1 by h cube into integral over minus infinity to infinity, integral over minus infinity to infinity, integral over minus infinity to infinity, e raised to minus beta px square plus py square plus pz square by 2m into dpx dpy dpz into integral over minus infinity to infinity, integral over minus infinity to infinity, integral over minus infinity to infinity, e raised to minus beta a by 2 into x square plus y square plus z square into dx dy dz. So this is equation number 2. We know that integral over minus infinity to infinity e raised to minus alpha x square dx is equal to square root over pi by alpha. So this is equal to 1 by h cube into 2 pi m kt the whole raised to 3 by 2 into 2 pi kt by a the whole raised to 3 by 2. This is equation number 3. Taking all the constants outside and write it as c, we can rewrite z1 as z1 is equal to c into kbt the whole raised to 3 by 2 plus 3 by 2. So this is equal to c into kt the whole raised to 3. So this is equal to c into 1 by beta cube. So z1 is equal to c by beta cube. So ln z1 is equal to ln c by beta cube. So E is equal to minus dou by dou beta of ln z1. This is equal to minus dou by dou beta of ln c by beta cube. This is equal to minus 1 by c by beta cube into dou by dou beta of c by beta cube. So this is equal to minus beta cube by c into minus 3c by beta raised to 4, and this is equal to 3 by beta. So this is equal to 3 kt. So u is equal to n into e, that is equal to 3n kt. So the answer is 3n kbt. The next question is, a system of n non-interacting classical particles each of mass m is in a two-dimensional harmonic potential of the form V of r is equal to alpha into x square plus y square, where alpha is a positive constant. The canonical partition function of the system at the T temperature is dash. So here the non-interacting system means it is a system of free particles, and it is also given that V of r is equal to alpha into x square plus y square. This is equation number 1. So the Hamiltonian H is equal to p square by 2m plus V of r. This is equal to px square by 2m plus py square by 2m plus alpha into x square plus y square. This is equation number 2. So the partition function z1 is equal to 1 by h square into integral over minus infinity to infinity 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 e raised to minus beta px square plus py square by 2m plus alpha into x square plus y square into dpx dpy dx dy. So z1 is equal to 1 by h square into integral over minus infinity to infinity e raised to minus beta px square by 2m into dpx integral over minus infinity to infinity e raised to minus beta py square by 2m into dpy integral over minus infinity to infinity e raised to minus beta x square dx integral over minus infinity to infinity e raised to minus alpha beta y square dy. And we know that integral over minus infinity to infinity e raised to minus alpha x square dx is equal to square root over pi by alpha. So this is equal to 1 by h square into 2 pi m kt the whole raised to 1 by 2 into 2 pi m kt the whole raised to 1 by 2 into pi by alpha beta the whole raised to 1 by 2 into pi by alpha beta the whole raised to 1 by 2. So this is equal to 1 by h square into 2 pi m kt into pi by alpha beta. So z1 is equal to 2 pi square m square by h square alpha beta square. So Zn is equal to z1 the whole raised to n. So this is equal to 1 by h square into 2m pi square by alpha beta square the whole raised to n. But in the option 1 by h square is not given, but the most appropriate answer is option D. Next question is a gas of non-relativistic classical particles in one dimension is subjected to a potential V of x is alpha x, where alpha is a constant. The partition function is dash. H is equal to p square by 2m plus V of x, and here V of x is equal to alpha x. So this is equal to p square by 2m plus alpha x. Then the z1 is equal to 1 by h into integral over minus infinity to infinity integral over minus infinity to infinity e raised to minus beta px square by 2m into e raised to minus beta alpha x dx dp. So this is equal to 1 by h into integral over minus infinity to infinity e raised to minus beta px square by 2m into dp into 2 into integral over 0 to infinity e raised to minus alpha beta x dx. This is equal to 1 by h into 2 pi m kt the whole raised to 1 by 2 into 2 into e raised to minus alpha beta x by minus alpha beta. The limit starts from 0 to infinity. So this is equal to 2 by alpha beta h into 2 pi m by beta the whole raised to 1 by 2, and this is equal to 8 pi m by alpha square beta square h square the whole raised to 1 by 2. So this is the answer. The next question is, consider a gas of n classical particles in a two-dimensional square box of side L. If the total energy of the gas is E, the entropy is dash. We know that the partition function for n particles is equal to 1 by n factorial h power 2n. Here it is 2 dimensions, so we use 2n. For 3 dimension we use 3n. So here this is equal to 1 by n factorial h power 2n integral over e raised to minus beta e dq power 2n dp power 2n, and this is equal to z1 the whole raised to n by n factorial. For n equal to 1 in 2d, we can write d square q is equal to l square, this is equal to a, that is d square p is equal to 2 pi p dp. So here the partition function for a single particle is equal to 1 by h square integral over e raised to minus beta e l square 2 pi p dp, and this is equal to 2 pi l square by h square integral over e raised to minus beta e p dp. We know p square by 2m is equal to e, and then just differentiating this we get 2p dp by 2m is equal to de, that is de is equal to p dp by m, that is p dp is equal to m de. So this is equal to z1, that is equal to 2 pi l square by h square integral over 0 to infinity e raised to minus beta e m de. So this is equal to 2 pi l square m by h square into e raised to minus beta e by minus beta starting from 0 to infinity. This is equal to 2 pi m L square by h square into 1 by beta. For n particles in 2 dimension, we can write Zn is equal to Z1 the whole raised to n by n factorial. So this is equal to 1 by n factorial into 2 pi m L square by h square beta the whole raised to n. Then the energy for a single particle is E1 is equal to minus dou by dou beta of ln Z1. This is equal to minus dou by dou beta of ln of 2 pi m L square by h square beta. So this is equal to minus h square beta divided by 2 pi m L square into 2 pi m L square by h square into minus 1 by beta square. This is equal to 1 by beta, and this is equal to kBt. Then E is equal to n into E1, that is equal to n kBt. This is equation number 3. Then the Helmholtz free energy A is equal to minus kBt ln Zn. This is equal to minus kBt ln of 1 by n factorial into 2 pi m L square by h square beta the whole raised to n. And this is equal to minus kBt ln of 1 by n factorial plus n ln of 2 pi m L square by h square beta, and this is equal to minus kBt into minus ln n factorial plus n ln of 2 pi m L square by h square beta, and this is equal to minus kBt into minus n ln plus n ln 2 pi m L square kBt by h square. And we know that E is equal to nkt, that is E by n is equal to kt. So we can rewrite it as A is equal to n kBt ln minus n kBt minus n kBt ln 2 pi m L square by h square into E by n. And here we know that S is equal to minus dou A by dou t, and this is equal to minus n kb ln n plus n kb plus n kb ln of 2 pi m L square by h square into E by n. And this is equal to minus n kb ln plus n kb plus n kb ln of 2 pi m by h square plus n kb ln of L square E by n. We can write n kb plus n kb ln of 2 pi m by h square as S0. So this is equal to S0 plus n kb ln of L square E by n minus n kb ln. So this is equal to S0 plus n kb ln of L square E by n square. This is equal to S0 plus n kb ln of L square root E by n the whole square. That is equal to S0 plus 2n kb ln of L root E by n. So the answer is option C. The next question is, a system of n non-interacting spin-half particles is placed in an external magnetic field H. The behavior of the entropy of the system as a function of energy is given by dash. So here n is equal to n minus plus n plus, where n minus is the number of particles parallel to the field and n plus is the number of particles is anti-parallel to the field. So the energy of n plus is mu h and n minus is minus mu h. So energy is equal to n plus mu h minus n minus mu h. This is equal to n plus minus n minus into mu h. N plus minus n minus is equal to E by mu h. This is equation number 2. So n plus is equal to half into n plus E by mu h, and n minus is equal to half into n minus E by mu h. This is equation number 3. The thermodynamic probability is W is equal to n factorial divided by n plus factorial n minus factorial, and S is equal to kb ln W. So we know S is equal to k ln W, that is equal to k ln n factorial minus ln n plus factorial minus ln n minus factorial. This is equal to k ln n factorial minus ln n plus factorial minus ln of n minus n factorial. And this is equal to k into n ln n minus n plus ln n plus n plus minus n plus ln of n minus n plus n minus n plus. And this is equal to k into n ln n minus n plus ln n plus minus n plus ln of n minus n plus. So dou S by dou E is equal to dou S by dou N plus into dou N plus by dou E. We know that N plus is equal to N minus E by mu H. So dou N plus by dou E is equal to 1 by 2 into minus 1 by mu H is equal to minus 1 by 2 mu H. This is equal to K into dou S by dou N plus is minus ln N plus minus N plus into 1 by N plus minus N plus divided by N minus N plus into minus 1 plus N ln of N minus N plus into minus 1 by 2 mu H. Minus 1 by 2 mu H is the dou N plus by dou E part. So this is equal to K by 2 mu H into minus ln N plus ln of N minus N plus. This is equal to K by 2 mu H into ln of N minus N plus divided by N plus, and this is equal to K by 2 mu H into ln of N minus divided by N plus. And we know 1 by T is equal to dou S by dou E. This is equal to K by 2 mu H into ln of N minus E by mu H divided by N plus E by mu H. This is equation number 4. For E less than 0, this gives T is positive when N minus is greater than N plus. And when E greater than 0, T become negative when N minus is less than N plus. And when N minus is equal to N plus at high temperature, then E is equal to 0. So we can draw a graph between S by Nk versus E. When E equal to 0, the maximum value of S by Nk is equal to ln2. The energy corresponds to N plus particles is N mu H, and the energy corresponds to N minus particles is minus N mu H. When the energy is less than 0, the temperature is positive. That means the temperature increases and it reaches the infinity value. Then if the energy is greater than 0, the temperature is negative. That means it decreases. It decreases from minus infinity to 0. So the graph looks like a parabola. So this is the answer. The next question is, the entropy of a system is related to the accessible phase space volume by S is equal to Kb ln gamma, where E, N, V are the energy, number of particles and volume respectively. From this one can conclude that gamma, here S is equal to Kb ln gamma. In equilibrium, gamma is going to be maximum because system stays in most probable macro state. That is, a system is having the largest micro state. That is, here gamma is maximum. That means entropy is maximum. So the answer is option C. The next question is, a system of non-interacting spin-half charged particles are placed in an external magnetic field at low temperature T. The leading behavior of the excess energy above the ground state energy depends on T as. So here the spin-half particles is placed in the external field H. They can align along the field and opposite to the field. Here the interaction energy is equal to minus mu dot H. When the spin align parallel to the field direction, we can write the theta is equal to 0. So the energy E1 is equal to minus mu H. And then spin aligns anti-parallel to the field direction, we can write theta is equal to 180. That is E2 is equal to mu H. So here the partition function for a single particle Z1 is equal to summation over I into Gi e raised to minus beta Ei. Here Gi is equal to 1, that is equal to summation over e raised to minus beta Ei, that is equal to e raised to minus beta E1 plus e raised to minus beta E2, that is equal to e raised to mu h by kt plus e raised to minus mu h by kt. And here E is equal to minus dou by dou beta of ln Z1, that is equal to minus dou by dou beta of ln of e raised to mu h by kt plus e raised to minus mu h by kt. That is, E is equal to minus 1 by e raised to mu h by kt plus e raised to minus mu h by kt into e raised to mu h by kt into mu h plus e raised to minus mu h by kt into minus mu h. And this is equal to minus mu h into e raised to mu h by kt minus e raised to minus mu h by kt divided by e raised to mu h by kt plus e raised to minus mu h by kt. The excess energy above the ground level is U is equal to E minus E1, that is equal to we know E1 is equal to minus mu h. So this is equal to E plus mu h, and this is equal to minus mu h into e raised to mu h by kt minus e raised to minus mu h by kt divided by e raised to mu h by kt plus e raised to minus mu h by kt plus mu h, and this is equal to mu h into 1 minus e raised to mu h by kt minus e raised to minus mu h by kt divided by e raised to mu h by kt plus e raised to minus mu h by kt. And this is equal to mu h e raised to minus mu h by kt divided by cos h of mu h by kt. That is delta u is proportional to e raised to minus mu h by kt. That is mu h by k is taken as c, that is equal to delta u is proportional to e raised to minus c by t. So the answer is option C. Next question is a collection n of non-interacting spins Si where I is equal to 1, 2, etc. up to n is kept in an external magnetic field B at a temperature T. The Hamiltonian of the system is H is equal to minus mu B summation over I Si. What should be the minimum value of mu B by kBT for which the mean value Si greater than or equal to 1 by 3? Here H is equal to minus mu B summation over I Si. When spin is aligned parallel to B, E1 is equal to minus mu B, and when spin is aligned anti-parallel to B, E2 is equal to plus mu B. So the partition function for a single spin Z1 is equal to e raised to minus beta E1 plus e raised to minus beta E2, and this is equal to e raised to beta mu B plus e raised to minus beta mu B. The expectation value of Si is equal to summation over Si Pi, and this is equal to summation over Si is equal to minus 1 to plus 1 Si Pi, and this is equal to minus 1 into P minus plus 1 into P plus, and this is equal to minus P minus plus P plus. This is equation number 1. The probability of spin parallel to field is P plus is equal to e raised to minus beta into minus mu B by Z, and this is equal to e raised to beta mu B by Z. This is equation number 2. And for the spin anti-parallel to field, P minus is equal to e raised to minus beta mu B by Z. Substituting the value of 2 and 3 in 1, we get Si is equal to minus e raised to minus mu B beta plus e raised to beta mu B by e raised to beta mu B plus e raised to minus beta mu B greater than or equal to 1 by 3. That is 3 into e raised to beta mu B minus e raised to minus beta mu B greater than or equal to e raised to beta mu B. 3 e raised to beta mu B minus 3 e raised to minus beta mu B greater than or equal to e raised to minus beta mu B plus e raised to beta mu B. That is 2 e raised to beta mu B greater than or equal to 4 e raised to minus beta mu B. That is 2 e raised to beta mu B divided by e raised to minus beta mu B greater than or equal to 4. That is 2 e raised to 2 beta mu B is greater than or equal to 2. That is 2 beta mu B greater than or equal to ln2. That is mu B by kt greater than or equal to ln2 by 2. So the answer is ln2 by 2. The next question is, consider 3 icing spins at the vertices of a triangle which interact with each other with a ferromagnetic icing interaction of strength J. The partition function of the system at the temperature T is given by dash. Each spin can align either up or down. That is, first spin can have 2 possibility, second spin have 2 possibility, third spin have 2 possibility. That is 2 into 2 into 2. That is equal to 8 possibilities is there. So here it is a 3 spin ferromagnetic system. So it is a closed boundary condition. So H is equal to minus J into S1 S2 plus S2 S3 plus S3 S1. Here the spin up can be represented as plus 1 and the spin down can be represented as minus 1. For S1 S2 S3, if the value is 1 1 1, then H is equal to minus 3J. For minus 1 minus 1 minus 1, H is equal to minus 3J. For 1 minus 1 1, H is equal to J. For 1 minus 1 minus 1, H is equal to J. For 1 1 minus 1, H is equal to J. For minus 1 1 minus 1, H is equal to J. For minus 1 1 1, H is equal to J. For minus 1 minus 1 1, H is equal to J. So we can write Z is equal to summation over I Gi e raised to minus beta H, that is equal to 2 e raised to 3 beta J plus 6 e raised to minus beta J. The next question is, an atom has a non-degenerate ground state and a doubly degenerate excited state. The difference between the two states is E. The specific heat at very low temperature is given by dash. So for E equal to 0, G equal to 1. So for E equal to E, then G is equal to 2. Here it is given that beta E is greater than 1. We know Z is equal to summation over I Gi e raised to minus beta Ei, that is equal to e raised to minus beta into 0 plus 2 e raised to minus beta E, that is equal to 1 plus 2 e raised to minus beta E. This is equation number 1. And E is equal to minus dou by dou beta of ln Z, that is equal to minus 1 by 1 plus 2 e raised to minus beta E into 2 e raised to minus beta E into minus E, and this is equal to 2e e raised to minus beta E divided by 1 plus 2 e raised to minus beta E, and this is equal to 2e by e raised to beta E plus 2, and this is equation number 2. Cv is equal to dE by dt, and this is equal to 2e into minus 1 into e raised to beta E into minus E by kb t square divided by e raised to beta E plus 2 the whole square, and this is equal to 2 kb E square divided by kbt the whole square into e raised to beta E divided by e raised to beta E plus 2 the whole square. So we can write this as, we know beta E is greater than 1, that is beta E is equal to E by kt is greater than 1. So we can write e raised to beta E plus 2 as approximately equal to e raised to beta E. So this is equal to Cv is equal to 2 e square kb divided by kb square t square e raised to beta E. This is equal to 2 kb beta E the whole square e raised to minus beta E. The next question is, the partition function of the system of n Ising spin is Z is equal to lambda 1 raised to n plus lambda 2 raised to n, where lambda 1, lambda 2 are the functions of temperature but are independent of n. If lambda 1 is greater than lambda 2, the free energy per spin in the limit n tends to infinity is dash. Here Z is equal to lambda 1 raised to n plus lambda 2 raised to n. It is given that lambda 1 is greater than lambda 2. We know when n tends to infinity, we need to find the value of a by n. So we know a is equal to minus kt ln Z, that is equal to minus kt ln of lambda 1 raised to n plus lambda 2 raised to n. So this is equal to minus kt ln of lambda n raised to n into 1 plus lambda 2 by lambda 1 the whole raised to n. So when lambda 1 is greater than lambda 2, we can write lambda 2 by lambda 1 tends to 0, and this is equal to minus kt ln of lambda 1 raised to n, and this is equal to n kt ln of lambda 1. So we can write a by n is equal to minus kt ln lambda 1. So this is the answer. The next question is, the Hamiltonian of a system of n non-interacting spin half particles is H is equal to minus mu 0 b si z, where si z is equal to plus or minus 1 are the components of ith spin along a external magnetic field B at a temperature T such that e raised to mu b by kbt is equal to 2. The specific heat per particle is dash. So when the spin is parallel to B, then energy is equal to minus mu 0 b. When the spin is anti-parallel to B, energy is equal to mu 0 b. So here the partition function for a single particle Z1 is equal to e raised to beta mu 0 b plus e raised to minus beta mu 0 b. That is, Z1 is equal to 2 cos h beta mu 0 b. This is equation number 1. The average energy per particle is U is equal to minus dou by dou beta of ln Z1. That is equal to minus dou by dou beta of ln of 2 cos h beta mu 0 b. This is equal to minus mu 0 b tan h mu 0 b by kt. This is equation number 2. So Cv is equal to du by dt, and this is equal to minus mu 0 b sec h square mu 0 b by kt into mu 0 b by k into minus 1 by t square. So Cv is equal to k into mu 0 b by kt the whole square into sec h square mu 0 b by kt, and this is equal to k into mu 0 b by kt the whole square into 2 divided by e raised to mu b by kt plus e raised to minus mu b by kt the whole square. So here it is given that e raised to mu 0 b by kt is equal to 2, that is mu 0 b by kt is equal to ln 2. So Cv is equal to kb ln 2 the whole square into 4 divided by 2 plus half the whole square. This is equal to 16 by 25 kb ln 2 the whole square. Next question is, an ensemble of non-interacting spin-half particles is in contact with a heat bath at temperature T and is subjected to an external magnetic field. Each particle can be in one of the two quantum states of energy plus or minus E0. If the mean energy per particle is minus E0 by 2, then the free energy per particle is dash. Here the energies are plus or minus E0. So Z1 is equal to e raised to beta E0 plus e raised to minus beta E0. This is equal to 2 cos h beta E0. This is equation number 1. U is equal to minus dou by dou beta of ln Z1 and this is equal to minus dou by dou beta of ln of 2 cos h beta E0. This is equal to minus E0 tan h E0 by kt. This is equation number 2. Here it is given that u is equal to minus E0 by 2, that is minus E0 by 2 is equal to minus E0 tan h E0 by kt, that is half is equal to sin h beta E0 by cos h beta E0, that is half is equal to e raised to beta E0 minus e raised to minus beta E0 by 2 divided by e raised to beta E0 plus e raised to minus beta E0 by 2, that is half is equal to e raised to beta E0 minus e raised to e raised to minus beta E0 divided by e raised to beta E0 plus e raised to minus beta E0, that is e raised to beta E0 plus e raised to minus beta E0 is equal to 2 into e raised to beta E0 minus e raised to minus beta E0, that is 3 into e raised to minus beta E0 is equal to e raised to beta E0, that is 3 is equal to e raised to beta E0 divided by e raised to minus beta E0, that is e raised to 2 beta E0 is equal to 2, that is 2 beta E0 is equal to ln 3. And here a is equal to minus kt ln Z1, that is minus kt 2 cos h beta E0, that is minus kt ln 2 minus kt ln over e raised to beta E0 plus e raised to minus beta E0 by 2, that is equal to minus ln 2 by beta minus 1 by beta ln over e raised to beta E0 plus 1 by e raised to beta E0 divided by 2, and this is equal to minus ln 2 by beta minus ln minus 1 by beta into ln over e raised to 2 beta E0 plus 1 by 2 e raised to beta E0. This is equal to minus ln 2 by beta minus 1 by beta ln over e raised to ln 3 plus 1 divided by 2 e raised to ln 3 by 2. So this is equal to minus ln 2 by beta minus 1 by beta into ln over 3 plus 1 by 2 root 3. And this is equal to minus ln 2 divided by ln 3 by 2 E0 minus 1 by ln 3 by 2 E0 ln of 2 by root 3. This is equal to minus 2 E0 into ln 2 by ln 3 plus ln 2 by root 3 by ln 3, and this is equal to minus 2 E0 by ln 3 into ln of 2 into 2 by root 3, and this is equal to minus 2 E0 by ln 3 into ln 4 by root 3, and this is equal to minus 2 E0 into ln of 4 by root 3 divided by ln 3. Next question is, for a system of independent non-interacting one-dimensional oscillators, the value of free energy per oscillator in the limit t tends to 0 is dash. Here En is equal to n plus half into h cut omega, and we know Zn is equal to summation over a raised to minus beta En. Substituting the value of En here, we can write it as this is equal to e raised to minus beta h cut omega by 2 plus e raised to minus 3 by 2 beta h cut omega plus e raised to minus 5 by 2 beta h cut omega plus etc. And this is equal to e raised to minus beta h cut omega by 2 into 1 plus e raised to minus beta h cut omega plus e raised to minus 2 beta h cut omega plus etc. That is Z1 is equal to e raised to minus beta h cut omega into 1 by 1 minus e raised to minus beta h cut omega, that is equal to 1 by e raised to beta h cut omega by 2 minus e raised to minus beta h cut omega by 2. So Zn is equal to Z1 the whole raised to n, that is equal to 1 by e raised to beta h cut omega by 2 minus e raised to minus beta h cut omega by 2 the whole raised to n. And here a is equal to minus kbt ln Zn. This is equal to nkt ln over e raised to beta h cut omega by 2 minus e raised to minus beta h cut omega by 2. This is equal to n kt ln over e raised to beta h cut omega by 2 into 1 minus e raised to minus beta h cut omega. This is equal to n kt into ln over e raised to beta h cut omega by 2 plus ln over 1 minus e raised to minus h cut omega by kt. This is equation number 1. So when t tends to 0, h cut omega by kt tends to infinity, that is e raised to minus h cut omega by kt, this is equal to 1 by e raised to h cut omega by kt tends to 0. So equation 1 implies a is equal to n kt into h cut omega by 2 kt. This implies the free energy per oscillator, that is a by n is equal to h cut omega by 2. So this is the answer. Next question is, a closed system having three non-degenerate energy level with the energies E is equal to 0 plus or minus E is at temperature T. For E is equal to 2 kBT, the probability of finding the system in the state with energy E is equal to 0 is dash. So the energy level given here is minus E, 0 E. With the degeneracy G is equal to 1. We know that this is equal to summation over I gi e raised to minus beta ei. Here gi is equal to 1. That is equal to summation over I e raised to minus beta ei. So this is equal to e raised to beta e plus 1 plus e raised to minus beta e. That is equal to 1 plus e raised to beta e plus e raised to minus beta e. This is equal to 1 plus 2 cos h beta e. So when energy is equal to 0, the probability is equal to e raised to minus beta into 0 divided by summation over gi e raised to minus beta ei. This is equal to 1 divided by 1 plus 2 cos h beta e. And here it is given that E is equal to 2 kBT, that is E by KT is equal to 2, that is beta E is equal to 2. So this can be written as probability is equal to 1 by 1 plus 2 cos h2. So this is the answer. Next question is, two non-degenerate energy level with energy 0 and E are occupied by n non-interacting particles at temperature T. Using classical statistics, the average internal energy of the system is dash. So here the energy level given as 0 and E with the degeneracy G is equal to 1. So here the partition function Zn is equal to Z1 the whole raised to n. So here Z1 is equal to summation over G e raised to minus beta Ei. This is equal to 1 plus e raised to minus beta E. So Zn is equal to 1 plus e raised to minus beta E the whole raised to n. This is equation number 1. And we know internal energy U is equal to minus dou by dou beta of ln Zn. This is equal to minus dou by dou beta of ln over 1 plus e raised to minus beta E the whole raised to n. This is equal to minus n dou by dou beta of ln over 1 plus e raised to minus beta E. This is equal to minus n into 1 by 1 plus e raised to minus beta E into e raised to minus beta E into minus E. This is equal to n e raised to minus beta e divided by 1 plus e raised to minus beta e. This is equal to n e divided by e raised to beta e plus 1. So the answer is option A. The next question is, the rotational energy levels of a molecule are E is equal to h cut square by 2 I0 into L plus 1, where L is equal to 0, 1, 2, 3, etc. And I0 is the moment of inertia. The contribution of the rotational motion to the Helmholtz free energy per molecule at low temperature in a dilute gas of these molecules is approximately dash. So here E is equal to L into L plus 1 into h cut square by 2 I0. So here L is equal to 0, 1, 2, etc. The partition function Z rotation is equal to summation over GL e raised to minus beta EL. Here GL is equal to 2L plus 1. That is Z rotation is equal to summation over 2L plus 1 into e raised to minus beta h cut square by 2I0 into L plus 1. This is equation number 1. And this is equal to 1 into e raised to minus beta h cut square by 2 I0 into 0 when L is equal to 0. Then this plus when L equal to 1, the term is 3 e raised to minus beta h cut square into 2 divided by 2I0 plus when L equal to 2, the term is plus 5 e raised to minus beta h cut square into 6 by 2I0 plus etc. So this is equal to 1 plus 3 e raised to minus c beta, where c is equal to 2 h cut square by 2I0 plus 5 e raised to minus 3 c beta plus etc. So at low temperature 5 e raised to minus 3 beta terms get decreases so that it can be neglected. So Z rotation is equal to 1 plus 3 e raised to minus c beta. So this is equal to 1 plus 3 e raised to minus h cut square by I0 kt. So A is equal to minus kBt ln Z. This is equal to minus kBt ln over 1 plus 3 e raised to I h cut square by I0 kt. That is, this is equal to minus 3 kt into e raised to minus h cut square by I0 kt. So the answer is option D. Next question is, in a system of n distinguishable particles, each particle can be in one of the two states with energy 0 and minus C respectively. The mean energy of the system at temperature T is dash. Here the energy given as 0 and minus C. So there is n distinguishable objects. Here G is taken as 1. So Z1 is equal to summation over Gi e raised to minus beta Ei. This is equal to G1 e raised to minus beta E1 plus G2 e raised to minus beta E2. That is, Z1 is equal to e raised to beta E plus 1. This is equation number 1. Then E is equal to minus dou by dou beta of ln Z1. That is equal to minus dou by dou beta of ln over 1 plus e raised to beta E. This is equal to minus 1 by 1 plus e raised to beta E into e raised to beta E into E. That is equal to minus e raised to beta E divided by 1 plus e raised to beta E. This is equal to minus E divided by 1 plus e raised to minus beta E. So U is equal to N into E, that is equal to minus NE divided by 1 plus e raised to minus beta E. So the answer is option D. The next question is, the vibrational motion of a diatomic molecule may be considered to be that of a simple harmonic oscillator with angular frequency omega. If a gas of this molecule is at temperature T, what is the probability that a random picked molecule will be found in the lowest vibration state? So here the energy eigenvalue is C is equal to n plus half into h cut omega, where n is equal to 0, 1, 2, etc. And this is equal to summation over n equal to 0 to infinity e raised to minus beta En. And Gn is equal to 1 for simple harmonic oscillator. That is, Z is equal to summation over n equal to 0 to infinity e raised to minus beta into n plus half into h cut omega. This is equal to e raised to minus beta h cut omega by 2 plus e raised to minus 3 by 2 beta h cut omega plus e raised to minus 5 by 2 beta h cut omega plus etc. And this is equal to e raised to minus beta h cut omega by 2 into 1 plus e raised to minus beta h cut omega plus e raised to minus 2 beta h cut omega plus etc. So Z is equal to e raised to minus beta h cut omega by 2 into 1 by 1 minus e raised to minus beta h cut omega. This is equation number 1. Then for the lowest vibration, that is n is equal to 0. This implies at n equal to 0, E0 is equal to h cut omega by 2. Then the probability at E0 is equal to e raised to minus beta E0 by Z. And this is equal to e raised to minus beta h cut omega by 2 divided by e raised to minus beta h cut omega by 2 divided by 1 minus e raised to minus beta h cut omega. And this is equal to 1 minus e raised to minus beta h cut omega. So this is the answer. Next question is, an idealized atom has a non-degenerate ground state at 0 energy and a G-fold degenerate excited state of energy E. In a non-interacting system of n such atom, the population of excited state may exceed that of the ground state above a temperature T greater than E divided by 2 kb ln2. The minimum value of G for which this is possible is dash. So here two energy level is given, one is E is equal to 0 and another is E. And one has a degeneracy G1 is equal to 1 and another has a degeneracy G2 is equal to G. One energy level contains n1 number of particles and another energy level contains n2 number of particles. So the number of non-interacting atoms is equal to n. When T is greater than E by 2 kb ln 2, then N2 is greater than N1. So when T is equal to E divided by 2 kb ln2, then N2 is equal to N1. So here result is equal to summation over Gi e raised to minus beta e. This is equal to G1 e raised to minus beta e1 plus G2 e raised to minus beta e2. This is equal to 1 into e raised to 0 plus d into e raised to minus beta e. And this is equal to 1 plus e raised to minus beta e. This is equation number 1. So here the probability P1 denotes the probability that the ground state is occupied. So P1 is equal to e raised to minus beta into 0 by Z, that is equal to 1 by Z. Here P2 denotes the probability that N2 is occupied, that is P2 is equal to G e raised to minus beta e divided by Z. We know N1 is equal to N into P1 and N2 is equal to N into P2. So N1 plus N2 is equal to N into P1 plus P2, and this is equal to N. So when N2 is equal to N1, we can write NP2 is equal to NP1. So that is P2 is equal to P1. That is G e raised to minus beta e by Z is equal to 1 by Z. That is G into e raised to minus beta e is equal to 1. That is G is equal to 1 by e raised to minus beta e. That is G is equal to e raised to beta e. This is equal to e raised to 3 by kt. And here it is given that T is equal to e by 2 kb ln2. That is equal to e raised to e divided by k into 2k ln2 by e. So G is equal to e raised to 2 ln2, that is equal to e ln2 square, that is equal to 4. The question is asking about the minimum value of G for which the population of excited state may exceed that of the ground state above a temperature T greater than E by 2 kb ln2. So when the temperature is greater than E by 2 kb ln2, then N2 will be greater than N1. But when the temperature is equal to E by 2 kb ln2, we get the minimum value of G, that is equal to 4. So the answer is 4. Next question is the Hamiltonian of a system of 3 spin is H is equal to J into S1 S2 plus S2 S3, where Si is equal to plus or minus 1 4, I is equal to 1 2 3. Its canonical partition function at temperature T is dash. So here we need to find the value of the partition function. So here H is equal to J into S1 S2 plus S2 S3. For spin up, the value of S is equal to 1. For spin down, the value of S is equal to minus 1. So the value of S1 S2 S3 is, for 1 1 1, H is equal to minus 2J. For minus 1 minus 1 minus 1, H is equal to minus 2J. 1 minus 1 1, H is equal to 2J. 1 minus 1 minus 1, H is equal to 0. 1 1 minus 1, H is equal to 0. Minus 1 1 minus 1, H is equal to 2J. Minus 1 1 1, H is equal to 0. Minus 1 minus 1 1, H is equal to 0. And here result is equal to summation over Gi e raised to minus beta Ei. This is equal to 4 e raised to 0 plus 2 e raised to minus 2 beta j plus 2 e raised to 2 beta j, and this is equal to 2 into e raised to minus 2 beta j plus e raised to 2 beta j plus 4, and this is equal to 2 into e raised to minus beta j plus e raised to beta j the whole square minus 2 plus 4, and this is equal to 2 into 2 e raised to minus beta j plus e raised to beta j by 2 the whole square. This is equal to 2 into 2 cos h beta j the whole square. This is equal to 2 into 2 cos h beta j the whole square. This is equal to 2 into 2 cos h j by k bt the whole square. So the answer is option B. The next question is the Hamiltonian of a system of n non-interacting particles each of mass m in one dimension is H is equal to summation over I equal to 1 to n pi square by 2m plus lambda by 4 into xi raised to 4, where lambda greater than 0 is a constant and pi and xi are the momentum and position respectively of the ith particle. The average internal energy of the system is dash. We know that by equipartition theorem, each squared energy term contribute half kBt. Then the expectation value of pi square by 2m is equal to half kBt. Here EA is equal to lambda by 4 into xi raised to 4. Let lambda by 4 is equal to alpha, that is equal to alpha xi raised to 4. Then the expectation value of VI is equal to the expectation value of alpha xi raised to 4. If E is equal to alpha x raised to n, we can write x raised to n is equal to E by alpha and x is equal to E by alpha the whole raised to 1 by n. Differentiating this, we can write dE is equal to n alpha x raised to n minus 1 dx. That is dE is equal to ne by x into dx. That is dx is equal to x by ne into dE. So this is equal to e raised to 1 by n divided by n alpha raised to 1 by n e into dE. Substitute the value of k as 1 by n alpha raised to 1 by n. So dx is equal to k e raised to 1 by n minus 1 dE. So the expectation value of E is equal to integral over 0 to infinity E into e raised to minus beta e dx divided by integral over 0 to infinity e raised to minus beta e dx. So this is equal to integral over 0 to infinity e raised to 1 by n e raised to minus beta e dE divided by integral over 0 to infinity e raised to 1 by n minus 1 e raised to minus beta e dE. We know that integral over 0 to infinity x raised to n minus 1 e raised to minus ax dx is equal to gamma by a raised to n. So similarly we can write 0 to infinity e raised to 1 by n minus 1 e raised to minus beta e dE is equal to gamma of n divided by beta raised to n. So we can write E is equal to gamma of 1 plus 1 by n divided by beta raised to n plus 1 divided by gamma of 1 by n divided by beta raised to n. So this is equal to 1 by n into 1 by beta. So this is equal to kT by n. Here energy is equal to alpha x raised to 4. So the power of x is 4. So n is equal to 4 here. So E is equal to lambda by 4 into x raised to 4. That is equal to kBT by 4. So the average energy per particle is equal to half kBT plus kBT by 4. This first term half kBT is contributed by the first energy term in the Hamiltonian, and the second is contributed by the second term, that is lambda by 4 xi raised to 4 in the Hamiltonian. So this is equal to 3 by 4 kBT. So the answer is 3 by 4 kBT. The next question is the energy levels accessible to a molecules having energy E1 is equal to 0, E2 is equal to delta, E3 is equal to 2 delta. A gas of this molecule is in thermal equilibrium at temperature T. The specific heated constant volume in the high temperature limit varies with temperature as dash. So here the energy given is E1, E2, E3, that is 0, delta, 2 delta. So here Z is equal to 1 plus e raised to minus delta by kt plus e raised to minus 2 delta by kt. So we can write E is equal to summation over I equal to 1 to 3 ei e raised to minus beta ei divided by summation over I equal to 1 to 3 e raised to minus beta ei. So this is equal to E1 e raised to minus beta E1 plus E2 e raised to minus beta E2 plus E3 e raised to minus beta E3 divided by e raised to minus beta E1 plus e raised to minus beta E2 plus e raised to minus beta E3. That is C is equal to 0 plus delta e raised to minus beta delta plus 2 delta e raised to minus 2 beta delta divided by 1 plus e raised to minus beta delta plus e raised to minus 2 beta delta. So Cv is equal to dE by dt. This is equal to 1 plus e raised to minus beta delta plus e raised to minus 2 beta delta into e raised to minus beta delta into delta by kt square plus 2 e raised to minus 2 beta delta into 2 delta by kt square minus delta into e raised to minus beta delta plus 2 e raised to minus 2 beta delta into e raised to minus beta delta into delta by kt square plus e raised to minus 2 beta delta into 2 delta by kt square divided by 1 plus e raised to minus beta delta plus e raised to minus 2 beta delta the whole square. So at the high temperature kt is greater than delta, then e raised to minus beta delta is approximately equal to 1 minus delta by kt and e raised to minus 2 beta delta is approximately equal to 1 1 minus 2 delta by kt. So Cv is equal to delta square by kt square into 1 minus beta delta plus 4 into 1 minus 2 beta delta into 1 plus 1 minus beta delta plus 1 minus 2 beta delta divided by 1 plus 1 minus beta delta plus 1 minus 2 beta delta the whole square minus delta square by kt square into 1 minus beta delta plus 2 into 1 minus 2 beta delta into 1 minus beta delta plus 2 into 1 minus 2 beta delta divided by 1 plus 1 minus beta delta plus 1 minus 2 beta delta the whole square, and this is equal to delta square by kt square into 5 minus 9 beta delta into 3 minus 3 beta delta minus 3 minus 5 beta delta into 3 minus 5 beta delta divided by 3 minus 3 beta delta the whole square, and this is equal to delta square by kt square into 15 minus 42 beta delta minus 9 plus 30 beta delta divided by 9 minus 18 beta delta. Here beta delta is less than 1. So here we can neglect the beta delta term and beta delta square term. So this is equal to delta square by kt square into 6 by 9, and this is equal to 6 delta square divided by 9 kt square. So this is the answer. That means the specific heat is proportional to 1 by T square. So the answer is option D. This is the end of this video. Thanks for watching this channel.